So I'm not that famous, right? So let me introduce myself first. So I'm Bo, working at YMSA. First, I would to thank Professor Yao who give me a job 2 years ago. So I'm a few people who can come here and working with Yao. Okay. So okay, in my age. Okay. So I would say my advisor was Jiaping Wang. So he shared me. Okay, I would say on behalf of my advisor, Jiaping Wang, because Jiaping Wang was, the same was Jiaping Wang's postdoc mentor. So on behalf of my advisor, Jiaping Wang, so we would like to convey our best wish to Professor Liang Semo on his 80th birthday. So let's come back to the talk. So our first talk is given by Professor Wei Ping Zhang. His title is Literature Evaluation Theory Revisited. So let's join me welcoming the Professor Zhang.
Thank you for the introduction. It's a great honor to be able to give a talk in this important conference. I will thank the organizers, especially Professor Yao, for the kind invitation. So today my title is Lichter's vanishing theorem. This is a famous theorem concerning scalar curvature. And we all know that scalar curvature is a basic invariant for Riemannian manifolds. A fundamental question in Riemannian geometry is to study when a smooth closed manifold can or cannot carry a Riemannian metric of positive scalar curvature. Moreover, there are well known that roughly two standard methods in studying this kind of problems. One is the minimal surface method pioneered by Xiong and Yao. The other is to use Dirac operators and their single index theory. In this talk, we will describe some applications of the Dirac operator method, as well as some generalizations to flat bundles and or foliations. So we start at the very basic concept that if we give a Riemannian manifold of dimension n, then for any point p with a small number, positive number r, we take a small ball around this point. Then we compare the volume of this small ball with the volume of this small ball in the Euclidean space. Then when the r tends to 0, we have this asymptotic formula. This formula determines the function, function every point a number, and then determine a function on the manifold. This KTM we call the scalar curvature. A classical result is that at least when the dimension of the manifold is greater or equal to 3, then for any smooth function, we should take one point. At one point, take negative value. Then there always exists a Riemannian metric such that the scalar curvature is equal to this function. So the natural Riemannian question is what happens if the function to be positive, and in this case, the first obstruction is provided by this Dirac operator method. Beyond, of course, in dimension 2, one can get results from Gauss-Bonnet. But for higher dimensions, the first obstruction comes from Dirac operator method. Indeed, the origin of the Dirac operator goes back to a long time ago. When Hamilton discovered quaternion, he wrote explicitly this the first line formula that the square of a kind of first order differential operator is equal to the Laplacian. And he indeed claims in his paper that such a formula will play important role later in mathematics and physics. It turns out that his claim is very correct. So many years later, Dirac constructed in the four-dimensional Lorentzian space his operator, and he used this Clifford called a polymetrics verifying the so-called Clifford relations. And then, many years later, T.R. Singer generalized Dirac's idea to on spin manifolds to construct a general Dirac operator on spin manifolds. So to be more precise, we start with Riemannian spin manifold. The spin condition is a topological condition. I will not go into detail. I will assume, for example, for simplicity, first that the manifold is of even dimension. Then with this metric and the spin structure, take a spin structure, one can construct a bundle of spinors. So STM, in the even dimensional case, it is a splitting S plus plus S minus, and it carries an emission connection. In the most general case, we also take emission vector bundle E, and carrying with emission connection, and we denote RE its curvature. Then a T.R. Singer's Dirac operator can be defined by the following. And small ei is the local orthonormal frame, and such a sub C is the Clifford action acting on the spinor bundles. But here we tested this bundle E, and this expression sum does not depend on the choice of the orthonormal basis, local orthonormal basis. So it's a well-defined. It turns out well-defined first elliptic differential operator. And if we restrict the D plus, D minus to the positive part and the negative spinor part, it exchanges the negative part and the positive part. And that's a adjoint relation, which means that the total DE is self-adjoint. Then one can define the index equal to the dimension of the kernel D plus minus the dimension of kernel of D minus. Here, originally the classical index is the minus dimension of the co-kernel of D plus. But here, with this adjoint property, we can replace by its kernel. And this self-adjoint property is very important. Then the famous T.R. Singer index theorem says that the index of this analytically defined operator can be expressed as in a topological way, where the right-hand side, if you use Chen-Wei representation, Chen-Wei theory can be expressed as an integration of such a differential form, complicated differential form. This A hat class and the Chen character of E. Here, the spin condition, it turns out essential because, for example, CP2, the A hat genus is not an integer. So this index theorem plays many important roles in many problems in geometry and topology. An earlier application is due to Lichtenowitz. So for this, because if you have a Dirac operator for geometry, we just can do the square. For example, Weissenberger formula and Buchner formula. For this spin Dirac operator, Lichtenowitz observed that this square equal to the Buchner Laplacian plus the scalar curvature over 4. And this Buchner Laplacian is well known to be non-negative. So then the Lichtenowitz theorem states that if on a spin manifold you have a metric with positive scalar curvature, then the A hat genus will equal to 0. So the proof is almost one line, because if you have a positive scalar curvature, then by the Lichtenowitz formula, D square will be positive. D square positive means that the kernel of D is 0. So the index of D plus would be equal to 0. Then on the other hand, by the T.R. Singer index theorem, the index D plus is exactly equal to A hat genus. So you get immediately that the vanishing of the A hat genus. So the theorem itself is very interesting because the condition is geometric, the scalar curvature. And the conclusion is that the topological is A hat genus, about A hat genus. But the proof, you need deep analysis. You need a T.R. Singer index theorem. So it's the application itself that combines this analysis, topology, and geometry. So this gives the first obstruction in for example, in dimension 4, that gives the obstruction of this A hat genus. if A hat genus is not 0, then, for example, on K3 surface, not there's a K3 surface and a manifold, spin manifold A hat genus, then it cannot carry metric of positive scalar curvature. And later, so the problem that later for this obstruction means that the next result I want to mention is that Gromov-Lawson and Stoltz. So Gromov-Lawson's result says that for every simply connected non-spin closed manifold of dimension larger or equal to 5, it always carries a metric of positive scalar curvature. The proof uses this surgery method initiated by Shun and Yao. And then Stoltz later solved the Gromov-Lawson conjecture. He proved that a simply connected spin manifold of dimension larger or equal to 5 carries a metric of positive scalar curvature if and only if the topological alpha invariant is equal to 0. In dimension 4K, this alpha invariant is exactly the A hat genus. So for simply connected manifold of dimension larger or equal to 5, the question of whether a manifold can carry a metric of positive scalar curvature, you get a reasonable satisfied answer. For non-simply connected manifold, the simplest example is torus. Here, the first breakthrough is due to Shun Yao, who proved that T3 has no metric of positive scalar curvature. And they use the minimal surface method, and at that time can prove to the dimension less or equal to 5. Then later, Gromov and Lawson using Dirac operator method by some generalization of Lichtenau's strategy to prove the higher dimensional case. So here that the Dirac operator, and also we'll see some deformed Dirac operators will also play some role in the study of the scalar curvature problem. So the next result I want to describe is a strong generalization of this Shun Yao and the Gromov-Lawson's theorem. Is due to LaRue in 1998. It says that if we have a closed spin manifold, and if there exists a map from M to the standard unit sphere of the same dimension, which is area non-decreasing, which means if you have a two form on the sphere, then you pull back the two form, the norm will less or equal to 1. Or if you have a region, you map it that if in reasonable sense, the area will be non-increasing. And assume that this map has non-zero degree, and assume that its scalar curvature verifies this inequality, that the scalar curvature larger or equal to n minus 1. This n is the dimension of the manifold. Then f is an isometric. F is a isometric. You can see easily that this statement implies the torus statement. Because on a torus, if you enlarge somewhat, you can get a map. You can get a map if the torus have a positive scalar curvature. If you enlarge the torus, you can get a map from the torus verifying this condition, but it's not isometric. So you get a contradiction. So this one is a generalization, a strong generalization, as I said, of this Gromov-Lawson and Shun Yao result. The proof is that following this Gromov-Lawson's idea is that you take the spinor bundle on the sphere, then you pull back the bundle as a twisted bundle. Then you consider the twisted Dirac operator. Then you apply the Lichtenau's formula at least in the dimension even case, you can get something. You can prove the result. I'll not go into detail. And then if n is odd, you usually do not have this index. But LaRue introduced a trick that it multiplies this manifold with a large circle. to reduce the problem to the even dimensional case. Even dimensional case. So the natural question is, as Gromov asked, is how about the non-compact case? How about the non-compacts? In an earlier version of his recent the 4 lectures, Gromov proposed a non-compact generalization to complete manifolds of this Larousse theorem. So we take M, a non-compact complete Riemannian spin manifold, and assume that the map from M to the unit, that the map from M to the unit sphere is area non-increasing, which is locally constant near infinity. That means outside a compact set, it is a local constant. And we assume that its degree is non-zero. Degree is non-zero. And also assume that the scalar curvature is larger or equal to the same inequality, larger or equal to n and n minus 1 on the support of this df. But outside of this df always 0. So it's a locally constant. On the support of df, he made this example. Then he asked whether one has that the infimum of KTM is strictly less than equal, less than 0. And indeed, Gromov point out that if one uses Gromov-Lawson's relative index theorem, I will mention this theorem later, it is easy to prove that the infimum of KTM under this condition is less than equal to 0. That means the metric cannot have uniformly positive scalar curvature. And the strict inequality means that it cannot carry metric of positive scalar curvature. So on compact manifold, these two are equivalent. But on non-compact manifold, the scalar curvature can be decayed without a uniform lower positive bound. So this is different. This is different. So this one I've solved this Gromov's the problem is that I proved the following. The result is that for even dimensional manifold under the same condition, is indeed that there will be no scalar curvature, no positive scalar curvature. So here, as I mentioned, the Gromov using Gromov-Lawson's result, we can prove easily that the inequality is less than or equal to 0. So to get out to remove this equality, we will obviously have to get some refined version of Gromov-Lawson's relative index. This I will describe in what follows. It's a very easy extension. Indeed, a general algebra strategy is that on a spin manifold, you consider a Z2 graded emission vector bundles. The psi equal to psi plus and psi minus is Z2 graded. Then we take a V, a self-adjoint odd endomorphism. Odd means that it exchanges psi plus and psi minus. Then we consider the Z2 graded tensor product. We use a hat, the d psi with this coefficient psi. Then the d plus and d plus part, the plus spin part will be s plus tensor psi plus and plus s minus tensor psi minus. And the minus part of the bundle is S minus tensor psi plus and S plus tensor psi minus. So this is a graded positive part and graded positive negative part. So for NAT, T, a real number, I introduce deformation, the dt plus the d plus tv. Then you can compute the square. It's a square equal to d squared plus t. With this bracket, this is Z2 graded bracket. This is d psi v plus v psi. Instead of this usual bracket, it's a Z2 graded bracket and plus t square v square. And the middle term, the coefficient of t, is indeed the bounded term. So now we assume we have a complete manifold, and we also assume that this V square has a positive lower bound near infinity. That means outside the compact subset, you have positive number such that the V square is larger or equal to delta. positive. And we also assume near infinity V identifies these two vector bundles. So with this result, bracket equal to 0. Then with this bracket equal to 0, then this middle term disappear. Outside the compact subset disappear. So then you can say that outside the compact subset, this dt square is uniformly bounded from below. Below we have this positivity near infinity. Then this property implies that the kernel of dt will be finite. The dt will turns out to be a Fredholm operator, and then you can compute its index. So the relative index term in this case is that the index dt equal to the right-hand side. The right side integration is over the non-compact space, but you see that outside the compact subset, this psi plus the psi minus are identified. So the difference of these two differential forms, if you use Chen-Wei representation, vanishes outside the compact subset. So actually, the integration of the right-hand side, if you use Chen-Wei theory, is the integration over a compact subset. So it's meaningful. It's well-defined and meaningful. So this is a general relative index term for this deformed Dirac operator without, I would mention, without any assumption on the scalar curvature near infinity. So now originally if we consider Gromov-Lawson situation, Gromov-Lawson assumes that the scalar curvature of a complete spin manifold, the scalar curvature has a positive lower bound near infinity outside the compact subset, and this psi plus psi minus are trivial vector bundles outside the compact subset. So then we go one more step. We compute this d square. We compute d square by using Lichnow's formula. So then the dt square will be a Bochner Laplacian plus the scalar curvature plus the t square v square near infinity outside the compact subset. Then under Gromov-Lawson's condition, that the right-hand side is larger or equal to a positive number. Positive number does not depend on t. So we can take t, move t to 0. You still have a positivity, uniform positivity near infinity. And then in this case, that the dimension of kernel of kt is finite without does not depend on t. So it's finite. It's for any of t, it's a Fredholm operator. So we can take t equal to 0. This is exactly what the Gromov-Lawson considered. Then in this case, the relative index states that Gromov-Lawson's relative index states that when t equal to 0, the dt psi split to two operators. So the relative index in the right-hand side is the index of dt, d plus of psi plus minus index of d plus coefficient with psi minus. Both are well defined due to the positivity condition of scalar curvature, and the right-hand side is the same. So I just remind that in Gromov-Lawson's theorem, they need the uniform positivity of the scalar curvature near infinity. So then we can prove this theorem I just recall here. And the proof is that also the method is standard that if we have a map from M to Sn, then following La rule, we take a spinor bundle. We take now the full spinor bundle, Z to greatest data space, the psi, pull back the spinor bundle. And then we also take a vector field on because it's even dimensional, so we can always take a vector field with only one 0 point. One 0 point, we assume that this point does not lie on the image of the non-compact part of the manifold. I mean, outside the compact part, the map is locally constant, so image is only a finite point. So we can always take this p does not belong to this finite point. So in this way, I also take the Clifford action of this vector field on the spinor bundle of the sphere. Then we pull back this Clifford action. So since x is non-zero. Non-zero is non-zero near the in the image of the infinity. So this V is invertible as a uniform lower bound, invertible near infinity outside the compact manifold. So we can always then we can do this deformation. This deformation here inside of T, I put epsilon because I will want to make epsilon very small. I want to make epsilon very small. Compute is square, and compute is square. Then near the support, we can use the additional formula and the Larousse argument. And outside near infinity, we can use this V squared, which has a lower bound, uniform lower bound to control. Then we use some argument to glue this infinite part and the compact part, glue together with some careful gluing estimate. You can finally get the positivity of the dt squared, and you can get this condition. You can get this get a contradiction if you assume if you assume that the inequality is not strict. You can get to it. As I mentioned, that here we use the trick. We take epsilon very small perturbation instead of usually in the index theory we take a large t to make an information. So this completes the even dimensional part. The even dimensional part of this theorem. For all dimension, the usual trick. For all dimension, the usual trick is to multiply a large scale, a large circle. But here, in doing this estimate or in doing this gluing of the compact and the non-compact part, you met problems. It's not, there's a correction term due to this large circle. That O1 over R, this term where R is very large, is also very small, but you do not get immediately the desired result. So what I could get at that time is that we need in the all dimension, the condition we need the KTM is strictly larger than n minus 1. N minus 1. So this left a remaining problem that whether this condition, the red condition, the strict inequality can be replaced by the larger and equal. So this is a problem I left at that time. And several years later, with my colleagues Li Yihan, Su Guangxiang, and Wang Xiangsheng, we can resolve this problem. That even for all dimensions, this Gromov, the question is still has a positive answer that we can refine this original inequality. We can put this original condition, this one. So to prove this, one need to work directly on all dimensional manifold. On all dimensional manifold, do not multiply a large circle. If you multiply a large circle, you can get there will be obstructions, even though small obstructions occur. And on the other dimensions, the method on all dimension index theory, the standard method is to use spectral flow. And use the eta invariant to compute this spectral flow. And even for all dimensions, even in the compact set, even for the compact case, this has not been done before, because the control of spectral flow using this additional formula still has some delicate part. And the first success is due to Li Han, Su Guangxiang, and Wang Xiangsheng. They gave a direct proof of Larousse theorem in all dimensions. This is also a question proposed by Gromov in his four lectures. So in the compact set, they managed to give a direct proof without using this multiplied large circle for the Larousse original theorem. Then to generalize this one, they use spectral flow, eta invariant. I think this is the first time Lichten's formula applied to all dimensions. And then to generalize this to non-compact set, one tautologically wants to develop spectral flow and the eta invariance for non-compact manifolds. This will be a big industry because you want to generalize. If you cut by the hypersurface near infinity, you still need to consider spectral flow and eta invariant for manifold with boundary. So it will be a very big industry. It's very interesting. Still, I think these three young persons are dealing with it. But for the special case, for this special case, we always need to some index. So not need necessary to use such a heavy machine of eta invariant. So we can glue, because near infinity scalar curvature no longer play very serious roles. So we can glue near infinity using this V to control carefully that you finally can reduce the problem to a computation on a compact manifold. And on the compact manifold, we can use spectral flow and eta invariance to make this control and combine with this, of course, with the spectral flow and eta invariance will be for the deformed Dirac operator I mentioned before, the D plus epsilon V, not the standard Dirac operator. Then you can make you need to do some careful estimate. You can conclude this result. So it turns out that the Gromov-Lawrence Gromov question, both in even and odd dimension, now have a complete solution. That we have a generalization of Larousse theorem to non-compact complete spin manifold. So this is Larousse theorem generalizing on one dimension. The other one is that another simple application of this relative index theorem is that here again we do not assume the uniform positivity of the scalar curvature near infinity. So in a joint paper with Wang Xiangsheng, we can we can prove the following result: if M is a closed spin, the so-called, I will not go into detail, the so-called area enlargeable manifold, and N is a non-compact spin manifold, then there will be no complete metric of positive scalar curvature on this connect sum. So it's well known that for us, for simplicity, it's well known that the torus is an enlargeable spin manifold. So the corollary is that for any non-compact spin manifold, its connect sum with torus cannot carry complete metrics of positive scalar curvature. This is a version of so-called non-compact version of the so-called Garrosh conjecture. If you use Gromov-Lawson's original relative index, it's relatively easy to prove that such a connect sum cannot carry a complete metric of uniform positive scalar curvature. But here that with our new relative index, we can replace this, remove this uniformity property, the conclusion. And indeed, such a theorem is interesting, and it's not so easy, because the first result when n equal to 3, the manifold spin, is due to Yao and his collaborator Lesod and Unger in 2020. And then almost the same time, I don't know the detail, is that Chadoshi and Li Cao and can prove such a result for dimension less than or equal to 7, and this for any manifold, not necessarily spin. And later I was told that Chadoshi and collaborator can make it to up to 11 dimensions. And in most recent preprint by Shi Yuguang and his collaborator, they can do it in a 12 dimension. They can do it in 12 dimension. So this means, so what I want to point at this time is that a simple refinement of this Gromov-Lawson result can get some interesting new result. And then Then next, I will talk another kind of generalization. This is the theorem I joined with Jianqing Yu. So we take a real flat back bundle over closed manifold. Closed manifold. That means a real flat bundle means it has a connection such that the curvature equal to 0. But the connection need not preserve any metric. Need not preserve metric. Then the result is that if F is a flat back bundle over closed spin manifold, opposite Riemannian manifold, spin manifold, opposite scalar curvature, then the following inequality, we have following vanishing result is that A hat Tm coupled with this Euler class of this flat back bundle equal to 0. This generalizes this relational theorem to involve any flat back bundle. So that's a famous example of Milne. See that if we have a genus G bigger or equal to 2, the sigma G, then there is a flat back bundle over this sigma G with non-vanishing Euler class. With non-vanishing Euler class. So if you apply a theorem, you immediately get a well-known result that sigma G is a hyperbolic manifold cannot carry a metric or positive scalar curvature. This will be, of course, this is a well-known result, but using this theorem, you get a very heavy machine proof of this very easy classical result. Anyway, and for me, I personally like this result because it put my two favorite classes, A class and the Euler class, put it together. And the main difficulty here is that to prove such a theorem, main difficulty here is that the connection need not be unitary Euclidean, need not preserve any metric. So for take any metric, we can get in a standard way the Euclidean connection by plus its adjoint and divided by 2. Then usually we have seen that we need to consider self-adjoint operator, Dirac operator. So the Dirac operator, for the simple Dirac operator, the D is associated with this kind of connection. So if we consider this property, twisted Dirac operator, you take the square, there will be a term that scalar curvature plus another term C, RF. So if you want to do similar estimate, that you can see that the main difficulty is that the scalar curvature does not control this extra term. So you cannot make it directly. Of this, of course, does not control of this term. So if you want to prove the more sophisticated bundle, which will produce the Euler class, such difficulty will also appear. So usually you cannot do directly. But the real solution is here that we use a method of Kohn. Alan Kohn, he did it in the case of foliation. I will mention is that you instead of consider one metric, you consider all metrics. You consider all metrics on this flat back bundle. Then it will be a bigger space. That you do the index theory on this bigger space. Because you finally you can prove this result. And so this is for the Euler class for flat back bundle. So for flat bundle, all the bond charging class vanishes. Euler class is here you have a non-trivial problem. Then for flat bundle, there are also very famous standard order Chern character, order Chern classes. So then we make for order manifold the following conjecture is that for the order Chern class, for the order spin closed manifold, then the nabla F minus its adjoint will be a one form endomorphism. So you can multiply it and take trace. You get closed form. It will represent the Orton class. Orton class. I made a conjecture that if there will be a metric of positive scalar curvature on spin manifold, then the A hat class paired with Orton class will also equal to 0. And this is widely open because on all dimensions such a pairing does not so far does not have a needed index theoretical interpretation. Not as in the Larousse theorem. As that case, we can have a Dirac operator to consider. Here is missing piece. So now we go back to Alan Kohn, which I mentioned. The Kohn's vanishing theorem is that it's Kohn's extension to formulations. So for any subbundle of tangent bundle, we take an integrable subbundle. Integral subbundle means that if you have two sections of this bundle, then the Lie bracket is also belong to the section of this bundle. Yeah, they use this condition by probing theorem. From any point, you can have a maximal piece of some manifold such that the F restricted to this piece is exactly the tangent bundle of this manifold. Then we call this a formulation. From any point, you have a leaf, the submanifold of a maximal rank F. Then Kohn outline proof of his famous theorem that if we have a closed oriented formulation such that the integrable subbundle is spin. At that time, if you have a metric on the total manifold such that its restriction to each leaf has positive scalar curvature, then Kohn claims that the genus will be equal to 0. So if F is equal to Tn, then this is exactly Lie theorem. And in the fibration, in the simplest fabrications, in the fibration cases, you will need to use this Tersinger's family index theorem. Usually you need to do this. And Alan Kohn wants to generalize this situation to the formulation case. So his proof ultimately uses this cyclical homology, non-commutative geometry, and the Kohn-Skandalis longitudinal index theorem, which is a far-reaching generalization of Tersinger's family index theorem. So nature question for geometry is that whether there is a possible direct geometric proof. And I learned this question from Kefeng Liu, who was then a student of Yao. Professor Yao asked Kefeng Liu, and then Kefeng Liu visited Nankai. We worked on this problem together for a while. And in the simplest case, in the fibration case or in the Riemannian formulation case, we can get a new proof. But here the main difficulty is that for Alan Kohn, he assumed only the integral bundle is spin. So the total manifold may not be spin. So if you want to work directly on total manifold, we want to overcome first this difficulty. The total manifold is not spin. Only a subbundle is spin. For this purpose, we introduce what we call sub-Dirac operator, which works exactly for that a subbundle is spin. And we can do this in some for Riemannian formulation, for fibration, we can get a direct proof of Kohn's vanishing theorem. But the nature to generalize to the more general case, we met a question that similar to the flat bundle, that in the flat bundle case that the connection may not preserve any metric. Such a difficulty also originally occurs in Kohn's original approach, and then Kohn consider the so-called Kohn fibration I just mentioned. But for time's sake, I will not go into detail, but I will only mention that. Yeah.
Have 2 more minutes.
Okay. Thank you. So I will can only mention such a proof can also lead to new results. For example, we can get an alternative generalization of this Lie formula. Since instead of as Kohn, we assume the integrable subbundle is spin. Now we assume total manifold is spin. The total manifold spin, the advantage is that you have a Dirac operator. You can get the same conclusion that if you have a Riemannian metric such that on spin manifold, you can restrict to each leaf has a positive scalar curvature, then still you get A genus equal to 0. And then you can apply this to torus, because torus is a spin manifold. We can get the result is that there is no metric. If you have any formulation on the torus, there is no metric on the torus such that it's a restriction to each leaf has a positive scalar curvature. For Alan Kohn, if you apply Alan Kohn, you need to assume F is spin. But here we can assume for any formulation. Of course, when F is the tangent bundle of the torus, it's exactly the original result of Xiong-Yao and the Gromov-Lawson. Finally, I want to mention that there's an open question nature open question in the formulation theory is that if we get for any formulation, if we have a metric on the total manifold such that the restriction on the leaf is positive, on each leaf is positive, then whether there exists a metric or positive coefficient on the total manifold, and need not be the original metric, whether there exists. And the answer, if we combine this loss and the Stokes result, and combine with my result, our result, then we can see that this answer has a positive, although indirect, positive answer for manifold of simply connected and with dimension larger than or equal to 5. And the general case is still open. So maybe some minimal method, surface method can using to construct directly such a metric, I don't know. But for Dirac operator, we only, so we can, to now we can only get this simply connected higher dimensional case. So I will stop here. Thanks a lot.
So is there any question for Professor Zhang? No.
Okay, so I want to ask something about the Laue argument. So in the Laue argument, we assume that F is like area non-increasing. So may I ask, we have another condition like Laue type argument such that is true for some other condition for eigen, like the singular value of F, like if we replace area non-increasing by something other.
I think this is essential if you have a, if you need to have a isometric rigidity part. The question is that I would also like to mention, if you make some weaker condition by replacing area non-increasing by using this length non-increasing is weaker, then in the three-dimensional case, Yu Guang Shi Yu Guang and its curvature has a proof using minimal surface. So for Laroussian, it's not say, usually say that you can only prove Dirac operator at least dimension 3 for the length non-increasing. One has a minimal surface method proof. And another condition, a reason that advances is that in 4-dimensional case, I think is there's a group led by Xie Zizang and it's Wang Jiming in the Science of China, Academy of Science of China, a group of people generalizes to 4-dimensional cases. 4-dimensional cases, the spin condition can be weakened in 4-dimensional cases. Yeah. But area increasing, I think it's essential here.
Yeah, Professor Zhang, I with Jimmy and Zhang, we proved the 4-dimensional.
Okay,
yeah.
Okay, you're good. Okay, good.
So any more questions?
Similar questions. Thank you, Professor Zhang. I want to ask you the motivation to consider the condition of the mapping from M to Sm1. I don't know whether the condition is something generalization or is this nature. I don't.
So yeah, you have a very good question. So I forgot to mention, because I mentioned the example of torus. Torus has a degree 1 degree non-zero map to the sphere. So if you apply the to the torus, you get immediately Xiong-Yao Gromov-Lawson's result. And indeed, Xiong-Yao's result works directly for, I think they first considered, they works for any manifold has a degree, non-zero degree map to sphere. Their method can apply to all this kind of method. A torus, for simply the torus has a degree 1 map to sphere. So you can apply to a lot of such manifolds. You can apply to a lot of such manifolds. And for Gromov-Lawson, they generalize the torus idea to so-called enlargeable manifold. You can get a lot of such a map. There's a lot of examples. You can have such a map, then you can have a meaningful result.
can I ask one more question?
Yeah, okay, last one.
Does there already exist some invariant on manifold that characterize the matrix that have positive scalar curvature? For example, the invariant vanishing or no vanishing characterize the result.
This is the originally this is Lichtenau's formula. You know, this H hat class is a characterization. If you can try to get more classes, it will be very good. It will be very good. This is a classical result. The right hand side H hat genus is the H hat class evaluation on the manifold. So it's a topological invariant characterizes geometrical property.
The Laplacian here is
No, the H hat genus is the last line. The H hat, so this is certain says if K is positive, then H hat genus equal to 0. So H hat genus is a characteristic number. This is classical result.
Okay, thank you. So since we don't have enough time, so let's finally thank Professor Zhang again. So do I need 4 minutes rest or just get started now? Okay, so let's get started now. So sorry. So our second speaker is Xiangyu Zhou from Chinese Academy of Science. So let's welcome Professor Zhang. Professor Zhou. Okay, sorry.
Thank you. It's my pleasure to give a talk here. First of all, I'd like to thank the organizers for the invitation. Today, I'd like to record some recent results in several complex variables. So first of all, let me recall very basic concepts in several complex variables. Actually, I think this concept is so fundamental as captured in differential geometry. So Pauli subharmonic function was introduced by Orca and Lalonde in 1940s. So a function is called Pauli subharmonic if it is up semi-continuous. Maybe take a volume minus infinity, and it's subharmonic when restricting on each complex line. So here we pay attention on the singularity of the function. So minus infinity. So very elementary example. Yeah. So here f1 and fk are holomorphic functions. So this is a very elementary example of Pauli subharmonic function. So as you know, so complex analytic subset is very basic for studying in complex geometry. So complex, the locally complex analytic subset is given by the zeros of f1, fk. This is holomorphic functions. So actually, so this is a special case of the singularities of this typical Pauli subharmonic function. So actually, in complex differential geometry, in Kähler geometry, so you know Kähler metric has a d-bar potential. Potential is strictly Pauli subharmonic function and smooth. So of course, for example, Bergman metric with this potential Bergman-Kernel. So this is basic examples of smooth Pauli subharmonic functions. So with a singular Pauli subharmonic function, we can define singular Hermitian metric on any holomorphic line bundle. So locally, it's given by e minus phi to power minus phi. So here phi is we can this is maybe not smooth. It's just locally integrable. So in this case, we can still define the cavity current. So dt buff phi, yeah. So it's still well defined. So in this way, we can define pseudo effective. This means cavity current is positive in the sense of this means phi is you can also define a bigger line band. Yeah, so this means the cavity current has a lower positive lower number. So Reynolds number is a purely subharmonic function. At one point, the Reynolds number is given by this formula. You know this is a very simple purely subharmonic function with the singularity at the point x. So you can also define a higher Reynolds number. You can define complex Mondial pair operator in current sense. Yeah. So you can define this wedge product. So you can take the mass. So this is also called higher Reynolds number. So in particular, when J is the dimension A, so this is the so-called complex Mondial pair mass. So another invariant is given by complex singularity exponent. In algebraic geometry, this is called LCT. So this is given by the supremum of this non-negative real numbers, such that this function is locally integral. So recently, with my former students, Deng Fusen, Li Yingji, and the Deng student, Liu Qunhuan and Wang Ziwei, we introduced the following concept. So we consider this function truncated in some sense. Yeah, this truncated. So if this LTT is finite, yeah, if this number is finite, Then we have this relation between the higher numbers, higher Lagrange numbers. So in particular, if the Lagrange number is 0, so we can get the complex Monge-Ampere mass is 0. So in this case, we answer the so-called zero mass conjecture, which says that if this Lagrange number is 0, then complex Monge-Ampere mass is 0. Another important invariance is the so-called multiplier ideal sheaf. Yeah, so given a Breuer subharmonic function, so we can consider an ideal sheaf. This ideal sheaf consists of gems of homomorphic functions such that this function is locally integrable. So of course, to a pseudo-effective line bundle, we can also define the multiplier ideal sheaf associated to this metric. So if you replace 2 by p, so you get the so-called LP multiplier ideal sheaf. So it's well known that Ladle proved that this ideal sheaf is coherent. This is a very fundamental result. So with this result, actually you can give one sentence of proof about the statement. Locally integrable points of this function is an analytical subset. Yeah, because this set is just the zero set of the multiplier ideal sheaf. Yeah, the zero set of the multiplier ideal sheaf is equal to the support of this quotient sheaf. Yeah, since this sheaf is coherent, so the quotient sheaf is also coherent. So as you know, support of a coherent sheaf is an analytical subset. And also, multiplier ideal sheaf is also integrally closed. And here we also have a Ladle vanishing theorem. So this says that if this bundle is a big line bundle, so for example, on a weakly pseudo-convex compact color, including a compact case, so you can get this vanishing theorem. So here you have a multiplier ideal sheaf. So in particular, if phi is smooth, if this bundle is positive, so this means phi is smooth. Phi is smooth, of course, this multiplier ideal sheaf is trivial. So this reduces to Kodaira vanishing theorem. So actually, this vanishing theorem also generalized Kawamata-Fiweg's vanishing theorem in 1980s. So joined with my former student Meng Xiankui, yeah, he was also a postdoc at Tsinghua. Yeah, we can drop it the color assumption. Yeah, so for if X is homomorphic convex, we can consider a big line bundle. So if we have this lower bundle, yeah, so epsilon is a positive continuous function. So we still have this vanishing theorem. So with Ladle vanishing theorem, multiplier ideal sheaf could be used to give a unified proof of Levy problem in several complex variables, and the Kodaira embedded theorem in algebraic geometry. So in this way, several complex variables and algebraic geometry come together again. So on multiple ideal sheaf, there was quite a famous conjecture due to Desmahis. So one can consider this union of multiple ideal sheaves. So with the coefficient bigger than 1. So since this is sheaves are lottery, so you can get this equality for some positive epsilon naught. So the Desmahis conjectured that this sheaf is actually equals to the multiple ideal sheaf. Yeah. So actually, the meaning of the conjecture says that if this function is locally integrable, then there exists positive lambda such that this more singular function is still locally integrable. So in another equivalent reformulation, yeah. So this real set actually is an open interval. So actually, so you have a very basic origin from calculus. So you know, so if this function with some power 1 over this function is locally integrable at the origin, you can see this power slightly bigger. This function is still locally integrable. So we actually have this very basic, very well known origin from the calculus. Yeah, of course, in high dimensional several complex variables, this Pauli subharmonic function is much more complicated. Yeah, you know, this is a very simple example of subharmonic function for complex variables. So when the multiple ideal sheaf is trivial, so that is to say, if this function is locally integrable, then under these assumptions, this was proved by Benson. For the general case, the general strict stronger openness conjecture in lower dimension, yeah, in one-dimensional case, this is well known, yeah. So in the dimension 2, yeah, this was proved by Farley, Johnson, Mustat in these papers. So about 10 years ago, we proved that this Desmahis stronger openness conjecture is true. Yeah, with my former student Guan. Yeah, he's now at Peking University. So actually, in the same paper, we also prove the following two forms. So one form is as follows. So this we can take a general Pauli subharmonic function, an increasing sequence of Pauli subharmonic function, which is convergent to a Pauli subharmonic function phi. So we still have this equality. And another case, so we can consider two Pauli subharmonic functions. So psi may be not necessary to phi. So we still have this strong openness, this equality. So this paper was published in 2015. So actually, our proof is based on our study systematic study on optimal L2 extensions problem. First, joined with my former students Guan and Zhu Lanfeng. Yeah, he's now at Wuhan University. Yeah, more than 15 years ago. Yeah, so we wrote a series of papers, and then with Guan and with Zhu, we solve more and more general cases. Yeah. So in several complex variables, so actually it's well known that we have about the extension theory. Where first of all we have Oka-Gadan. Yeah. So extension theory. So this means given a subvariety in a Stein manifold, any holomorphic functions on this subvariety can be extended holomorphically to the holomorphic functions on the Stein manifold. Yeah, so actually, so this is equivalent to Gadan's theorem B. So actually, this theorem, of course, very fundamental, plays a very fundamental role in several complex variables. So actually, so this was used by Searle to establish Gaga principle. So in 1980s, so Osawa Takegoshi got L2 extension theorem. So combining the Hormander's L2 methods for solving D-bar with L2 estimates. So this theorem was used by Yongtong Xu and many others to solve important conjectures. For example, the deformation invariance of privilege general, yeah, which is a fundamental result in birational geometry. So we have further developer will get optimal L2 extension. So actually optimal L2 extension there is also a geometrical property. So the relative canonical bundle has some positivity. Yeah. So actually, so this was used in recent works by Hakon Popper-Schiller about the Itaka conjecture and singular positivity of higher direct images by Takayama, and also recently by Owen Hall, yeah, about the BDPP's unirule criteria. Yeah, this BDPP's unirule is for projective algebra case. Yeah, so now this result is extended to compact Kähler case. So a compact Kähler manifold. So it's uniruled if and only if this canonical bundle is not pseudo effective. So we also has a immediate consequence of the stronger openness. We have the following vanishing theorem. So we consider a pseudo effective line bundle on compact Kähler manifold. So so we can define the numerical dimension of this pseudo effective line bundle. So we still have this vanishing theorem for Q bigger than this lambda. So in particular, if this line bundle is big, then the numerical dimension is just A. So this reduces to Liddell vanishing theorem. And we also has the following corollary. So for a big line bundle, we have this equality. So here, this SIF is the so-called asymptotic multiplier ideal. This is defined in algebraic geometry. So this is a maximum member of the family of ideals. This by this linear system. And here H mean, yeah. So this is given by Desmai's theorem. So this theorem says that for a pseudo-effective line bundle, one always has a unique singular Hermitian metric with minimal singularities. So this was conjectured by Desmai, Lawrence An, and Lazarsphere, and it was also listed as an open problem in Lazarsphere's book. Actually, the solution of Desmai's strong openings conjecture is also used in recent work about the new approaches to Yao-Tian Donaldson conjecture. So for example, in Berman, Buxton, Johnson's paper, so actually the main results rely on the strong openings. And in another paper by Davas Zhang, then discuss a general set. So X is a compact color. The anti-canonical bundle is not necessarily positive. Is just B. So in this theorem, he then used the strong openings as the starting point. So now let's recall some fundamental theorem about two existence. So first of all, this is due to Homander. Now you know the advantage of Homander's two method is to use PSH weights. So actually, this PSH weight could be regarded as a singular metric on the trivial line bundle, such that this trivial line bundle is pseudo-effective. Yeah. So for example, we can recall an example of Homander's two existence theorem as follows. So D is a bounded pseudo-convex domain. Phi is a Purely subharmonic function. Then we can solve D bar equation, with this L2 estimate. So you can see this E minus phi actually. So this is a singular metric on the trivial line bundle. Yes, such that this trivial line bundle is pseudo-effective. And so Homander's L2 existence for line bundle case could be extended to vector bundle case. So due to Desmai. So let me recall some basics. So here X omega is a Hermitian manifold. So E is a Hermitian homomorphic vector bundle. So we have a chain connection. So we can naturally define chain curvature. So locally with the coordinate and locally frame, so we can write this curvature, chain curvature as follows. So to this form, we have this Hermitian form on E value the tangent bundle. So it's natural to define Lacanau positive and also Griff's positive. Yeah. And if you take dual, so you can get negative Griff's and negative Lacanau. You can define such concepts. So this is for smooth Hermitian metric on homomorphic vector bundles. Yeah. So this are well known. So now let's recall Desmai's two existence theorem. So we consider this vector band, Hermitian vector band. So we consider this curvature operator. This is curvature. This is Lefschetz operator. So if this curvature operator is semi-positive, definitely on this E volume, and so we can solve this D-bar equation. Yeah, we can solve this D-bar equation with this L2 estimate. Yeah, so this is was done by Demailly. So with my former students, we studied the converse of L2 existence and L2 extension. Yeah. So in several papers. Yeah. A couple of years published. Yeah. And also Hosono Ilayama also followed our work to give some interesting result. So now let me recall a case about the converse of Osawa-Takegoshi L2 extension theorem. So here phi is just the upper semi-continuous. Yeah. If this LP extension if P is 2, so if this L2 extension holds from one point, then actually this function is PSH. So Osawa-Takegoshi L2 extension theorem says that if phi is a Bruder subharmonic function, then we have this L2 extension from one point. So we got the converse of his theorem. And for vector bundles, we also get a similar converse. So we can get actually this vector bundle is Griff's semi-positive in the singular sense. Later I will explain the definitions of singular metric and singular Griff's positivity and singular Lacaro positivity. So a couple of years ago, with my former students, Deng Fusen, Ning Jiafu, yeah, and once we introduced the following concept. So actually, this means locally we can solve D-bar equation with L2 estimate. Yeah, so this means locally we can solve D-bar equation, vector bundle volume with this L2 estimate, with L2 estimate. So then we get the converse of the Homander-Demailly's L2 existence theorem. So we get that this vector bundle, Hermitian vector bundle is L2 optimal if and only if this metric is Lacaro semi-positive. So as you know, if H is Lacaro semi-positive, then the curvature operator actually the curvature operator is semi-positive. Yeah. So this is an easy calculation. So curvature operator is semi-positive if and only if the curvature is Lacaro semi-positive. Yeah. So this is a simple observation. So of course, yeah, the if part, if H is Lacaro semi-positive, so this is due to Homander and the Demailly. Yeah. So we got the converse. So in this way, we get a bridge between the intersection of several complex variables with d-bar equation, and this intersection of several complex variables with a complex differential geometry. So we get this connection, a bridge. So with this theorem, so actually we can solve Lampert's problem about complex geometry on vector bundles. Yeah. So Lampert's problem sets as follows. So he asked whether a Hermitian metric which is a limit by increasing sequence metrics of Lacalo semi-positive. This limit metric is still semi-positive or not. So as you know, directly by the definition, yeah, you cannot get since the curvature involves higher derivatives. Yes, you cannot from if a sequence of function has a limit, we cannot get the derivatives still have a limit, have the limit. So but with our theorem we can get the following simple way to solve this conjecture. So since this is Lacalo semi-positive, so of course this is L2 optimal. So this means locally we can solve this d-bar equation with this L2 estimate. So we can solve. So here we can get this is Hj. Yeah. So but you can find that by simple calculation. So this condition L2 optimal condition preserves under the increasing sequence limit. So when Hj goes to H, so you can still solve this d-bar equation and get this to estimate for the limit metric. So this is to say this limit metric is also to optimal. So and then you using our theorem, so we can get this limit metric, the Lacalo semi-positive. Yeah. So in this way we can solve this Lampert's problem. So now let's recall. Yeah, for light bundles, we already define a singular metric. We also have some positivity concept. So for example, pseudo effective. So now and then people generalize this concept to the vector bundle case, and then we can see it's easy to define a singular Griff's semi-positivity. Later, I will explain you how to define singular Lacalo semi-positive. So for singular metric, so you can get the so-called multiple submodule shifts. So this is a vector bundle version of multiple ideal shift. So of course it's natural to ask some questions about multiple submodule shifts as light bundle case. So singular metric. So first of all, singular Binsler metric. You can get so this of course this metric satisfies the homogeneity property, and this norm is measurable. Yeah. So for some measurable section. So of course this so here so H is not necessarily smooth. So of course you also define Hermitian metric. So if you have a inner product, Yeah. So if this is measurable Hermitian metric on this point minus this pore set, so you can define this singular Hermitian metric. So the following vector is well known for smooth Hermitian metric on vector bundle. So H is smooth glyphs semi-negative if and only if this items are equivalent. So if this function is purely subharmonic for any holomorphic section, and this log also purely subharmonic. So in this way, yeah, you can define singular glyphs semi-positive. Since you can define for singular metric, this is still well defined. Yeah, if so, you can consider this function is a singular purely subharmonic. So in this way, you can define singular glyphs semi-negative and glyphs semi-positive. Yeah, and with our result on characterization of Lacalo semi-positive, so it's also very large to define a singular Hermitian metric of semi-positive Lacalo semi-positivity. So we can say a singular Hermitian metric is a singular Lacalo semi-positive if this metric is singular glyphs semi-positive, and H is L2 optimum. Yeah. So here, of course, you can also use 2 as the definition, but in this way, yeah, you know, for smooth metric, Lacalo semi-positive implies glyphs semi-positive. So you can naturally define this concept for singular metrics as this way. So for singular metric on vector bundles, so you can define multiple submodule sheaf. So this sheaf consists of gems such that this norm is locally integrable. So of course, if E is just a Lie bundle, so this is just a multiple ideal sheaf. Hosono and Ilayama prove that this sheaf associated to a singular Lacalo semi-positive metric is coherent. Yeah. So this is a coherence theorem. So for Lie bundle case, this the multiple ideal sheaf is coherent. This is due to Lido. Recently we prove the following result. So actually for this sheaf, we still have strong openness and stability. So this is vector bundle version of Desmai's strong openness conjecture. Yeah. So in this case, strong openness means as follows. So if we have a sequence, this a singular metric, yeah, and we have this convergence. So then we have this equality. So in particular, so we have this the union of these sheaves is equal to the multiple submodule sheaf. So here this is the determinant. So in the vector bundle case, this metric plays a basic role in the study. Finally, let me recall some applications. So let's recall, for vector bundle, we have a projectivist bundle. So and its tautological bundle is denoted by LE. So here pi is the natural projection. So it's well known that the direct image of this bundle times m times. So we have the symmetrical tensor power of the vector bundle. So
Professor Zhou, you have 2 more minutes. Yeah, I counted for you.
Kobayashi Ochai proves that this equality. Actually, the relative canonical bundle is given by this. So they prove this isomorphism. So this is a vector bundle. So here is a line bundle cohomology. So on the other hand, Le Bourdieu proof this is a holomorphic vector bundle. So reduces. So this isomorphism theorem establishes a connection between the cohomology of vector bundles and that of this line bundle case. So of course, together with Kodaira, Akizuki, Lacalo vanish theorem for line bundles, so this isomorphism also leads to Le Bourdieu vanish theorem for ample vector bundles. So recently we generalize both of these isomorphism theorems to singular bundle case. So we consider a singular bundle case. So in this way, we define singular Hermitian metric with some positivity. So we get some generalization. This is a generalization of Kobayashi Ochai. So here multiple ideal shifts. This is a multiple submodule shift, and this is a submodule shift. This is a multiple ideal shift. So in this way, if H is smooth, so for we can take a smooth function such that this is always strictly Lacalo semi-positive. So in this way, so we can get actually different proofs and generalize the theorem of Le Bourdieu and Kobayashi's isomorphisms. So we can also generalize Ladle vanish theorem to bundle case, and also homomorphic singular homomorphic Morse inequality for line bundle, and we can get to the case homomorphic vector bundle. So yeah, I stop here. Thank you.
So any question for Professor Zhou?
Professor, I'd like to ask a question about you mentioned higher the low numbers. So which I'd like to ask what to which class of functions are the low numbers defined, the higher the low numbers defined. So is it can it be defined for non-plurisubharmonic functions like M plurisubharmonic or something like that.
Yeah. So so here, so for some for some important class of plurisubharmonic function, the so-called singular class. So you can define a complex Mongian pair operator. Yeah. On such plurisubharmonic functions. So if you can define actually you for singular for singular class, you can define, for example, J is N, yeah, D bar 5. Yeah, so actually you can define for any J. So for such 5, yeah. So it's naturally you can define this wedge product, yeah. But here in this case, since we consider isolated singularity, so actually so for any plurisubharmonic function, you can define such wedge product. Yeah. So you can naturally get these lambdas. Yeah.
What is the geometric meaning of higher Lalone numbers when J is greater than 1?
Yeah, this is a good question. Yeah, actually, so this is the so-called how to say? Yeah, you know, this is actually is the so-called current. Yeah, so this is actually the so-called Lalone number of currents at the point. Yeah. So actually, Lalone number, yeah, you know, Lalone number. This is also geometric meaning. Yeah, you have also geometric meaning, and also you can consider you can consider this with some the same dimensional the volume of the ball, yeah, with the quotient, yeah, with the comparison, yeah. So yeah, there is some geometric meaning, yeah.
Okay.
Okay, can you ask after this talk? Okay, if you have any more questions. So we have 5 minutes or so let's come back at 11:15. So we have sorry.
In dimension bigger than 1, strictly bigger than 1, if you drop the condition, the plurisubharmonic function to be upper semi-continuity, but allow it to be true on almost every complex line, complex curve, but not globally. Can you tell us most things? Drop the condition of upper semi-continuity on the open set, but only allow it to be true on complex curve.
对，谢谢周先生，你这是一个现在为止还没有解决一个明的。Yeah, thank you for your question. Yeah. This is still open problem. Yeah, it's said. Yeah, this is still open. Yeah, I think. Yeah.
My voice can be heard. So let's come back at 11:20. Okay. Okay, please have a say. So our last talk is given by Professor Mark from University of Hong Kong. The title is Canonical Cantor-Einstein metric in relation to a rigidity theorem concerning irreducible lattice gamma in automorphism group of omega for omega of rank greater or equal to 2. Okay, let's welcome Professor Mark.
It's my great pleasure to be speaking here, witnessing the celebration of the 50 years of geometric analysis. I'd like to thank the organizers. A lot of my work has to do with uniformization and also with rigidity. Rigidity is also a kind of uniformization that is about characterizing complex structure. I'd like to provide some background for those who are not in the several complex variables. So first of all, on a bounded domain in Euclidean space, there exists a metric called the Bergman metric is based on the log-Puris harmonicity kernel, which is obtained from the square interval holomorphic functions. Now, in several complex variables, there's a replacement of the Poincare metric in one variable. That is the complete canonical Cantor-Einstein metric, constructed first of all by the Cheng and Yao back in 1980, based first of all on the solution of the Calabi conjecture. It was proven to be almost complete, and then there was an article of myself with Yao proving its completeness. So for some time, it has been my wish to give us an application of this replacement of the Poincare metric in several variables. So the reason why we get completeness is from the Schwarz-Lemma for volume forms by Yao, and an essential theorem in several complex variables, namely the Puris harmonicity of minus log delta, where delta is a distance function. This was mentioned in the talk of Professor just now. In the definition, this is possibly the first one of the first definitions of Puris harmonicity on the subject. So the Cantor-Einstein metrics on bounded domains, their existence also implies that the domain is a domain of holomorphism. Okay. Now, about rigidity results. So in 1987, I proved a uniqueness of the Hermitian, the canonical metric defined either by Bergman metric or the Cantor-Einstein metric on omega mod gamma, where omega is of rank at least equal to 2. I first proved this under some assumption, the assumption that there is a domination, that the metric given of semi-negative curvature is bounded by multiple of the canonical metric. I assume that H has non-positive curvature in the sense of Griffiths. This was obtained by a Gauss-Bonnet formula. So my first applications of Chern theory of differential forms. Okay, so how does one get this theorem? First of all, I have to specify a certain set. So suppose I have omega, like one bounded symmetric domain, is dual to the Grassmannian, and in the Grassmannian you have rational curves. The rational curves define the tangents, and the tangents define what is now called the variety of mean rational tangents. So if you take that set, you restrict that set to omega. Omega sits in compact dual. So omega sits in compact dual, and then I can do this integration. This was typo here. This S is the same as this Q. Q is a certain number defined by the dimension of the zeros of bisectional curvature. So you have this formula. G is the canonical metric, and H is a given metric, which is of semi-positive, semi-negative curvature. You can also replace this H hat by H hat plus G hat, because you can add two metrics belonging to this class, and it still belongs to the class. So you have this. So from here, from this integral formula, the important thing is that you have 0 here. The key point is, why does one have vanishing? This is not altogether clear, because when you take the first Chern class minus the first Chern class, the fact that you have the so-called characteristic direction or directions of the minimal rational curves give you that this has some 0 eigenvalue. But there's one thing to check, namely when you restrict to this subset. When you restrict to this subset and you descend to the quotient, this 0 eigen vectors still are tangent to the subspace. So you need to check something, and this I checked using the Haash-Chandra realization theorem. Okay, so I want to say something about the holomorphic isometries of the ball, and this will be used in what follows. Okay, so for some time I was interested for various reasons to study the question of holomorphic or analytic continuation of germs of holomorphic isometries. I was interested in such a problem because of a question raised by Clausel and Ulmo in holomorphic dynamics. They were interested in computing the commutant of certain Heck correspondence, and it turns out that this can be reduced to 2 different questions in differential geometry. And I solved this problem for the question of holomorphic isometry, and I solved another problem with Sui Chong on the holomorphic measure preserving maps. So today, what's essential is the isometry. Well, it's already done by Clausel and Ulmo. They make use of the seminal work of Calabi in studying holomorphic isometries into space forms. And this is the, I think it's the thesis of Calabi transformed into an article in which he defines the notion of the diastasis. Now, when I have a germ of holomorphic isometry, I can use the Berman metric or the Berman kernel to embed the domain into infinite dimensional space. So if I map from the, for instance, from the ball into omega or into D, then I can embed D into infinite dimensional space. I compose a map, and therefore I can use the result of Calabi about analytic continuation. And therefore, in interior continuation is no problem. What is the problem is on the boundary. When you do the embedding into infinite dimensional space, you don't see the boundary. Boundary is nowhere. It disappears. So then I devised a method still studying the holomorphic identities arising from equating the diastasis. The diastasis is something that is preserved under holomorphic isometries. So I studied the preservation of that. And then to cut the thing short, I just want to say that I was able to extend the map by introducing additional functional identities. If you have the equation of the diastasis, you can, as is usual in several complex variable, freeze one variable and get holomorphic identities, infinite number of them. But these identities might not cut the graph into the dimension you want. You have to add additional the constraints, and I was able to do that by introducing the extremal functions from the Berman kernel. These extremal functions might be characterized by maximality of first derivatives and so on. I was also able to provide a counterexample to a conjecture of Clausel and Ulmo, in which I was able to produce non-trivial isometries from a disk into P polydisk by writing down an explicit map. And the reason why this is an identity is because the potential functions agree. Of course, you have to guess what it is, and I guessed it for the first time, and that was the correct. Turns out to be miraculously the exam. I was actually trying to prove that their conjecture was correct until I realized that if certain asymptotics appear, then there might be a counterexample, and it was the counterexample. But for some time, I was curious on whether you have higher dimensions. So in 2011, when I wrote up a survey article on this, I actually posed a problem, whether there exists higher dimensional examples. You can have a ball embedded into a bounded symmetric domain, for instance, a priori, but you don't have a higher rank embedded into a higher rank because of metric rigidity, or the proof of Hermitian metric rigidity that I had already in '87. So then until I realized that suddenly, also because of other motivation like Arx-Lindemann type of theorems, I was able to find an example, and an example can be described actually geometrically as follows. The green region is actually the bounded symmetric domain, and this region is now embedded into the dual, the compact dual of omega. Take Q on as a boundary point. The boundary point, the regular part of the boundary point. The boundary has a certain stratification. I take any point, the regular part is equivalent to any other point. Take such a point and take the set of minimal rational curves, which are just the projective lines. So they lift in omega hat. Take the intersection with omega, and then you have a certain subvariety with the singularity and boundary. So inside omega, it is smooth. And I know that for holomorphic isometry, the image must be smooth. So this is style smooth. Then I checked that this thing has asymptotically the holomorphic bisectional curvature because strict pseudo-convexity at the other end. And then has a certain one-parameter family of homogeneity. And this implies that this is holomorphically isometric to the ball by the work of Calabi. Okay. So what is the relevance of this? The relevance of this is the following. Actually, I'm going to prove a certain rigidity theorem. This rigidity theorem about of higher rank into D mod gamma prime, where D is any bounded domain. Okay. So rigidity usually you have to do with certain geometric structure, and the method of harmonic maps would go from, for instance, a compact Kähler manifold into omega mod gamma. So I will be studying another problem, which is the opposite. So you have omega mod gamma into a more general class of manifolds of negative curvature. And how can you find such a general class? I will make use of bounded holomorphic function. So this was something new at the time of the work. So a bounded holomorphic function will induce what I call Carat-Theodori metric. This is the smallest intrinsic metric, so to speak. And this metric has negative curvature in the generalized sense. So Zhou Xiangyu was talking about Puris harmonicity and all that. And these are examples where you can have Finsler metrics, which are continuous and Lipschitz, and so they have log Puris harmonic potentials. But actually, these examples are not, or certainly not smooth, except in the case of the ball. So when you have a bounded domain D and you have a gamma prime, D mod gamma prime, this is already something with negative curvature. So I want to extend the range of rigidity phenomena by allowing the target manifold to be to carry negative curvature in some generalized sense. So this generalized sense can be in the sense of currentness, where Zhou was talking about. They could have, in this case, it's taking sup of Puris harmonic log absolute value of holomorphic functions. So in the case of a domain, the Carat-Theodori metric is always a complex Finsler metric, which is non-degenerate and has non-positive curvature in the sense current. Okay. So I'm going to study gamma equivariant holomorphic maps. So instead of saying omega mod gamma into omega prime or into D mod gamma prime, I can just lift the map. And so I study omega into D. So take a bounded symmetric domain of higher rank, or even an irreducible one, but with a gamma which is irreducible, like a polydisk. So you can study this. And this goes into omega you assume this is phi equivariant. So this is a map between gamma to gamma prime, and assume that this image is infinite. So I proved a theorem which was, well, when I did it, was also somewhat surprising, was the following. So first of all, I should say that the Hermitian metric rigidity theorem implies the following, implies that you have uniqueness of holomorphic maps. Because when the target n is negative or semi-negative in the sense of Griffiths, you just pull back the metric. You add the two together by the uniqueness of the Hermitian metric of curvature properties. This must be a multiple, and therefore f pullback of h is lambda minus 1 times g. So this is a holomorphic isometry. If this is scalar, it can follow from this that actually this is totally geodesic holomorphic isometry. But this requires a target which is of semi-negative curvature in the sense of Griffiths. And these are very hard to find. Of course, you can construct them from various constructions, starting with the bounded symmetric domain. But other than that, it's difficult to find one. I did make use of this, for instance, the study of the Modelville group of function fields, where you can have the Cougar family sitting over a Ziegler modular variety. This has a family of Hermitian metric, and it's not of semi-negative curvature, but it has an expansion, and the first term is semi-negative. And that was good enough, and that was the reason behind our vanishing theorem of the Modelville rank over function fields which are modular. This was work with Wing Canto in 1993. Okay, so then I raised this question: what can I say if I allow H to be a complex Finster metric of non-positive curvature? So, for instance, the Carter-Theodoric metric. So, a negative curvature means negative curvature in the sense of currents. You take log of this Hermitian metric. Well, a Finster metric is a Hermitian metric on the tautological line bundle. So you take log of the metric in local coefficients, and then you assume that is Chris harmonic function. Okay, so this is the theorem. The theorem is more general, but I will deduce a case where the target is just a bounded domain. So there are bounded holomorphic functions, the new element. So let omega be a bounded symmetric domain of rank at least equal to 2. This is decomposition, and then okay, and this gamma assumed to be a torsion-free irreducible lattice. So I assume this is big. So for instance, if you look at the modular moduli space, or for the well, abelian variety with real multiplication, you get into the Hilbert modular varieties, and these are varieties whose universal cover, these modular varieties are covered by the polydisk. And gamma is irreducible. It's like SL2 of some ring of integers, and it projects something dense in each of the factors. So I assume that in the target, so here I have the target n, and n tilde is uniformization. I assume that n tilde carries some bounded holomorphic function to the extent that when you get this map, pulling back from each factor, you get at least one non-trivial holomorphic function. This is certainly the case when I assume n tilde to be a bounded domain, but this is more general. Okay. Now, so under this non-degeneracy assumption, well, I was able to prove some rigidity theorem, but let me first maybe formally explain a little bit about the Finster metric rigidity. So Hermitian metric rigidity has to do with the Hermitian bilinear form. But actually, one can give a proof, and even in the finite volume case, with some assumption on the metric, like the current conditions, that actually you have Hermitian, you have Finster metric rigidity. So what does this mean? Finster metric only measures certain vectors along the minimal directions. Okay, I do not consider all directions. I only consider those along the minimal directions. Why are they important? Because for a minimal direction, there's an associated zero of bisectional curvature. In the other direction, you may not. So at a generic point, you don't have zeros, and therefore you can always perturb the Finster metric and still preserve the property. So you don't expect rigidity, but you can expect rigidity along certain special directions, at least for the minimal directions. And in fact, this could be proven. This can be proven by an adaptation of the original proof. You can make use of the integration by part and so on to the following geometric situation. I have a certain bundle over the omega mod gamma, and over this bundle, there's a certain foliation. This is a foliation by holomorphic varieties. But this holomorphic variety is a kernel of a first transform. The whole foliation itself is not holomorphic, the leaves are holomorphic. So what one can prove is that by the integration by part, even in the finite volume case, is that actually you can get that the metrics are proportional to the canonical metric on each leaf. And then you have to prove that there exists a dense leaf. When there's a dense leaf, then you have a global constant. The fact that you have a dense leaf comes from ergodic theory, comes from Moore's ergodic theory for semi-simple leaf groups. And Moore's ergodicity theorem will be used to a much larger extent in a moment. Okay, so the discovery was actually in several stages. So in about 20 years ago, I proved the Hermitian diffusive metric rigidity, and then I make use of it to prove a certain embedding theorem. The embedding theorem is the following. Suppose I have this equivariant map, and suppose the image of the fundamental group is non-trivial, then I prove actually when you lift to the space, to the universal covering, you have an embedding. So this was quite surprising because my condition was just that the image is the image of the fundamental group is non-trivial essentially. Yeah. So then I prove in that case that you have already embedding. The proof of that theorem makes use of Finster metric rigidity and extremal functions for bounded holomorphic functions. So when you have the rigidity, at least along the minimal direction, you know that pulling back the map, this is going to be at least a constant multiple of the canonical metric. So it means it's not zero, and therefore it's an immersion along certain directions. But along this direction do not cover the manifold, so you have to do some more work. You have to make use of what I would call extremal functions for bounded holomorphic function to do it. But the key point is the uniqueness along certain directions. Okay. Now, as to the separation of points, so immersion is easier. One just make use of Carter-Theodoric metric. But for the separation of points, it's more difficult, actually. The reason why it's more difficult is that, well, immersion is a local property. Separation is more 2 points which could be distant from each other. So I introduce a metric, a way of constructing a metric, which only works on the what I call this VMRT bundle. On this VMRT bundle, because you have product, you have this. I think Kangzhou is here. He knows the importance of the products. You have a product of a disk times a lower rank bounded symmetric domain, and then you can average the metric by the circle action. When you average, the semi-negativity is still preserved, but you only get this averaging along the direction that is special. For other direction, you don't get the averaging. But that is good enough. That was good enough for me to prove the embedding theorem. So here is the statement of the theorem. Well, here this is just recording why you can average. Average is sort of summing up with the weight, and this is an elementary calculus inequality, and it also follows the Gauss equation. Okay, so because of the embedding theorem, but this was some mid-stage development. This was already 20 years ago. So that because of that, I was led to raise the following question. Why do you get an isometry? So the D has no structure. D is just a bound domain, and you have omega mapping to D. And the only thing I know is that this is going to be a submanifold. It's not even known to be closed, a submanifold. So I was wondering whether there is stronger rigidity property, at least under the assumption that this map induces an isomorphism on fundamental groups. Okay, so my question is whether it is possible to project the image onto, so you have a domain D here. This is the image of F. So this might be close, but I do not know that's close. But I guess maybe it's possible to project all the image onto it. So this would be called an extension theorem. So what is an extension theorem? It says the following. How do I get this projection map? It suffices to say that f pulling back of the bounded holomorphic function will give me the identity map on the domain. So to prove that I can invert this map with the extension, it is sufficient, it's equivalent essentially, or certainly sufficient to prove that I can pull back the bounded holomorphic function and get the identity map. That would be the end of proof. And actually, if I can do that, I don't even need embedding theorem. Because the embedding theorem is sort of intermediate to propose, so to speak, to suggest that there is stronger rigidity. Okay, so with the technique I'm going to develop, this was done together with Kwok-Kin Wong, who is now at Shenzhen University. I was able to prove, we were able to prove two theorems. The one is the fibration theorem, the other is isomorphism theorem. So the fibration theorem is more general. I can deal with compact, well, I can deal with just n on which the universal cover n tilde carries sufficiently many bounded holomorphic function. And the isomorphism is more specific. I will be looking at n tilde being a domain, bounded domain D, or bounded domain in a Stein manifold. You can do that. And I will make use of Kähler-Einstein metric here. And the statement is the following. Suppose you have a map from X gamma to Y gamma prime, and which induces an isomorphism, then this must be a biholomorphic map under a certain assumption, namely that this has a finite Kobayashi-Eisenman volume form. This condition is always possible if you know a priori the X gamma prime is quasi-projective. But this is a more elementary condition, intrinsic volume that one imposes on this. So notice that this theorem is with the domain being X gamma, this being more general about the domain. And when you work with harmonic maps, it's usually the opposite direction, because you use the negativity of the manifold in order to get the heat flow in order to get harmonic maps, and then you prove the harmonic map is holomorphic under certain condition. So this goes in the opposite direction as the known methods on harmonic maps, starting with Yam-Tong Siu's DD-bar-Bochner-Kodaira formula. Okay. And another important thing about this is that, of course, if you talk about D being itself, let's say D being itself a bounded symmetric domain, then of course Margulis superrigidity, at least in the co-compact case, would imply that you have a total geodesic map and so on and so forth. But here, I'm not assuming any particular structure on D except that it carries bounded holomorphic function. And when you have D being omega prime, then it's a k pi 1. So omega prime mod gamma prime would be a k pi 1. So determining the fundamental group will also determine the homotopy types and so on. But in the case where I have an arbitrary domain D, I know nothing about the higher homotopy type. So the string of this theorem is that I impose only a condition on the fundamental group. But in its place, I have to assume the existence of bounded holomorphic function. So this is a new feature of my theorem with Wong. So this is a statement of Moore ergodicity theorem, which I already used. And I use this in a bit larger extent. And by, you can read Zimmer, a very good book, on which the theorem is stated. And then various ergodicity theorem implies various density theorems. And the density theorem would allow me to say, for instance, the foliation argument I had, that you have a leaf which is dense. Okay. Now, so let's now look at the situation where I have a bounded domain in general. So here is a lemma. The lemma is that in general, I cannot say that what is this group H? This is a hyperbolic flow. So I have this bounded domain, I have two faces of the boundary, and there's a flow from one to the other. This is just an embedding of SL2Z, and you take a hyperbolic flow, which is embedded. So you flow from one face to the other. So I do not know whether gamma H is dense, but Moore's ergodicity theorem tells me that gamma G exists for a generic choice of G. So after some the refinement, you can assume that gamma exists, and you work as if gamma times exists. So Moore ergodicity theorem says that ergodicity of the gamma action and of the H actions are equivalent to each other. Essentially, that's what it is. So so when H is non-compact, then the gamma action on G mod H is ergodic, and therefore you have a dense leaf. That's application Moore. So what is important here, when gamma H is dense, then it is possible to approximate gamma by H, or approximate H by gamma also. So you take H going a flow from one to the other, so it's dynamic, and you can approximate these elements by gamma up to small perturbation. This small perturbation go to identity map. So that is the point. Now, and then one has to consider the flows for all pairs of phases for which the flow is defined. And then we found out that actually it is easy to characterize. You take two maximal phases on the boundary, you would have a hyperbolic flow as I define it, if and only if their closures do not intersect. So we can parameterize all these pairs. I have to look at all possible pairs. The key point I'm going to point out is that I want to pull back holomorphic functions, and I want to make use of the boundary values of boundary holomorphic functions. And you can do it, but only generically. So you have to choose things properly. So these are the boundary values for boundary holomorphic functions. It says that, well, the Furstenberg and Korani, that when you approximate or go to a boundary of a ball, and you take, for instance, a boundary holomorphic function, then you have admissible boundary values almost everywhere. Admissible is non-tangentially, and these are in domains defined by the actually by the Kähler-Einstein metric. Now, so I studied the pullback of the vector space or Banach space or boundary holomorphic function from the target. So I have this D and I pull them back. So I do certain operations on that. What is allowed? What is allowed is, of course, you can compose it with an element of gamma. So this space is gamma invariant. The second, I can extract conversion series, a conversion sequence of such functions, but I am allowed to extract conversion sequence with respect to the Frechet topology, not with respect to Banach topology. So for instance, you can certainly get the functions which are continuous up to boundary. This is an invariant subspace. So I will say that I have a strongly invariant subspace if it's closed under extraction of conversion subsequence with respect to the Frechet topology. The C says that you can take average. You can take average with respect to any measure. Okay, so this taking average is essentially taking sums and extracting conversion subsequence. And then this is a technical thing which is very essential. So suppose I have a pair of these maximal phases, and I have a flow from one to the other by a hyperbolic flow, which I call H. Then you suppose to have, well, and then this phi C has certain conditions, but they are genericity conditions. And then suppose I have boundary values, then I can pull back the boundary values for one of the two boundary values. I have two phases, so I have a flow, so I have two endpoints. And then suppose I have boundary values everywhere, then I will be able to pull them back, either from this phase or from the other phase. I don't know which. And I do not know that both exist. I know at least one of them exists, according to Moore's ergodicity theorem. Okay. Now, but why do these boundary values exist? It's not clear whether the boundary values exist. Imagine, suppose I can pull back and get functions continuous up to the boundary, then everything is done. But I don't. The map is rather arbitrary. It's just holomorphic. When you pull back functions, you might not have boundary values, first of all. And if you have boundary values, they're just bounded functions. You don't know very much about it. So first of all, in order to say that when you pull back your boundary values, you have to make use of the fact that this embedding of the ball, actually, take this point and you will have, so use an arc, but this is actually a hypersurface, and this is the boundary of a ball. Since it's the boundary of the ball, you can make use of the theory of Furstenberg and Korany and say that the boundary value exists almost everywhere. But now you're not talking about a ball, you're talking about a face, and the face is sort of transversal to the ball. So you have to choose the boundaries properly so that I can get boundary values and almost everywhere on the boundary of the face. This is a rank R minus 1 bound symmetric domain transversal to the ball. And then if I choose properly, then I can pull things back. This can be done when you parameterize all KD projections to make use of the ball. I should say that I had this idea of doing things a long time ago, but I was uncomfortable with applying the theory of Poisson integers for semi-simple Lie groups because this is not well known to the community on several complex variables. So instead, after working on holomorphic isometry, I figured out that one can do it with the ball boundary, and this is well known. And you can read Rudin's book on this boundary value, for instance. It's very standard work, so you can do this. So this was not very important. The important thing is that I can pull back and get boundary values. I can get boundary values by choosing judiciously, and then I can average, because you have a product structure. You have this cross this lower rank R minus and bound symmetric domain. Into this, you have a circle. So you can take the average, and the averaging with some kind of linearization. So if you choose the function properly after composing by an element of the group, and the elements can be approximated by elements of gamma up to small errors. And so you can always choose such proper pulling backs. And when you pull this back, then the average would give you functions which are non-trivial function linear in one variable. So this is what you can do. And now you can also average over the k. So omega is G mod k. You can average over k. And average over k produce for you some actually linear function. And this linear function by Schur's lemma, if you choose things judiciously, would give you the identity map up to a constant. So that's the essential way that this argument goes. So this is, I think I explained the ideas first already, so I can jump a little bit. So this is the technical thing. So the theorem I had with Wang can be stated in the following thing. So if omega is a bound symmetric domain of rank at least 2, and gamma is an irreducible lattice, you take a vector subspace of H infinity omega, which is gamma invariant under the under the topology of convergence on complex subsets. Then the only invariant subset is H infinity. Now, certainly, if you take the Banach norm, you can take continuous function of the boundary that's invariant. So this is a counterexample. But if you allow convergence uniform on compact sets, which is what I did, then the higher rank implies that actually this is all of H infinity omega, provided it contains the constants. So I should say that in a rank 1 case, one can construct easy examples where this fails. But I do not know if it always fails in the case of the ball and gamma. I do not know. Now, then finally, I want to say a little bit about how the Kähler-Einstein metric is used. Okay, so I have this, I can invert this and can get projection map and so on. So you can imagine this is some kind of vibration. But omega goes into D, this might be lower dimensional. And then your vibration, and this vibration would have then positive dimensional fibers. Now I'm in a domain, and therefore these fibers would carry bounded holomorphic functions. The generic fiber of the projection, I'm going to prove by contradiction. The generic fibers are positive dimensional and they are smooth. Of course, there are some singular ones. I take a smooth one, and they have generically finite volume with respect to the induced Kähler, the restriction of the Kähler-Einstein metric. But on the Kähler-Einstein metric of finite volume, one does not have bounded holomorphic, holomorphic function, certainly. And so this gives a contradiction. The contradiction says that the fibers are zero dimensional. If the fibers are zero dimensional, already you get the isomorphism. That's good enough. Now, but then, well, why do I need the Kähler-Einstein metric? First of all, there's no canonical metric that's complete. I have to make use of completeness of the Kähler metric to do mathematics. And then I have a theorem also true for omega, not D, not necessarily a domain of holomorphy. So I do not have a Kähler-Einstein metric in general. But from D, I can always go to D hat. D hat is the hull of holomorphism studied by Oka and others. So this D hat carries, according to existence theorem of Kähler-Einstein metric, a complete Kähler-Einstein metric. So I can work with D hat, but I have to be able to know how D is related to D hat. So in our paper, we prove that D is actually D hat is actually univalent. It's not just a Riemann domain, and the complement of D hat of the complement of D in D hat is actually of measure 0. So what I prove for D hat, I can also imply that this is already valid for omega. So for D, so D is actually equal to D hat. So that's essentially the end of the proof. And this is where the Kähler-Einstein metrics make use of not on the domain, but on its hull of holomorphy. And I find quite satisfactory that one can make use of the KE metric and also several techniques from several complex variable, which are classical at the time of Oka. So thank you very much. And happy birthday to Professor Leon Sang.
So any question for Professor Mo?
How is the complex Finster metric be constructed for bounded symmetric domain?
Okay, now first of all, the Carl-Theodoric metric is 1. This is for any bound domain. For the bound symmetric domain, for the proof, for first proof of the embedding theorem, I need to have some averaging technique. So if you take a direction that's minimal direction, this is tangent to actually, well, you remember you had this cross omega prime. Omega prime is of rank R minus 1. So something in this direction will actually give you minimal rational tangent. Okay. Now, so what I do is then I average with respect to the circle in that direction. And then I get an average, and which is then defined only for the minimal directions. So this is a Finster metric. Is equivalent to a Hermitian metric defined on a subset of projectified tangent bundle. But this is good enough for my rigidity results. I always focus on this C, what I call Cx gamma, which is the defined as follows. You take the VMRT, the variety of minimal rational tangents, restrict to omega and mod out by gamma. This is always my setting.
Okay, thank you. Yeah.
So any more questions? So there is no more question. Let's thank Professor Mock again. So before you leave, I have a reminder. So our after session will move to Jianhua building. Okay. So please check the brochure and you can get the information. Okay. Not this room again in the afternoon.
talk title is on locally Chern homogeneous Hermitian manifold. Let's welcome.
Thank you very much. I'm honored to be here to report. The topic is a bit perhaps old. We're interested in spatial types of homogeneous space. So this is based on So our goal is to do differential geometry on non-Kähler complex manifold, compact complex manifold. So in differential geometry, we care about the shape of the space. For a given topological manifold, we want to know what kind of metric will have the simplest shape. And of course, the constant curvature spaces would be the simplest in that regard. So, for example, in Riemannian geometry, complete Riemannian manifolds with constant sectional curvature is called space forms. So their universal covers are these three: sphere, Euclidean space, and the hyperbolic space. So, a bigger class. So beyond the space forms, the bigger class is the so-called symmetric spaces, which means the local symmetry, the reflection, namely sending a point along the geodesic to opposite point of the anchor point. So that map is local isometry. If for every P, this reflection is a local isometry, we call this a locally symmetric space. And then an even bigger class is the homogeneous space, which means the isometry group acting transitively on the space, right? And since we care about compact manifold, we usually require the condition to be satisfied on the universal cover level, right? So downstairs, it's a quotient. Of course, symmetric spaces are automatically homogeneous because if you have 2 points, giving 2 points P and Q, you want to have an isometry sending P to Q. All you have to do is to join P and Q by a minimum geodesic and find the midpoint, right? And then the reflection about the midpoint will send P to Q, right? So, locally homogeneous space is automatically locally symmetric. So by locally homogeneous here, we mean the universal cover is homogeneous. So for symmetric spaces, the characterization is given by Cartan's theory. This is a famous theorem, namely, the local symmetry, which originally is defined by the reflection map to be isometric, can be characterized by a pointwise condition on the curvature, namely the Levi-Civita connection whose curvature is parallel under the Levi-Civita connection. So this is a necessary and sufficient condition. And of course, the set of symmetric spaces are fully classified because of the classification on semi-simple Lie algebras. And then for homogeneous space, there is a parallel analogous characterization. This is the theorem, famous theorem of Ambrose and Singer in the 1950s. So the statement says that if you have a complete, simply connected Riemannian manifold, how do I know it's homogeneous, right? Suppose I don't know anything about the isometry group. Then I just need to check a pointwise condition, namely, if you have a metric connection D, which is not necessarily the Levi-Civita connection, if this connection has parallel torsion and curvature. So here, so T is a torsion defined by taking well, basically measures if the connection is symmetric, right? Using the Lie bracket as the background. And the curvature is the usual 2-1 tensor, a 3-1 tensor. So if both curvature and torsion are parallel, it's like they're constant in some sense, right? And then the space is homogeneous, and vice versa. So this is the famous theorem of Ambrose-Singer, and also later on by Constant, who also contributed. So, so in the literature, people will call this kind of metric connection Ambrose-Singer connection. Otherwise, it's just too long to describe, right? So Ambrose-Singer means both T and R are parallel. So their theorem can be rephrased as being homogeneous, being locally homogeneous means the existence of an AS connection. So here, I would like to give a remark. So despite the, well, these two theorems, Cardan theorem and Ambrose-Singer theorem looks very, looks analogous, but there's actually a difference between the set of symmetric space and the set of homogeneous space. Namely, symmetric space is fully classified. So we kind of, you can write down the list, so you know what they are. So their geometric properties are also well behaved and can be checked. But a homogeneous space, on the other hand, in my opinion, is not very well understood. It's certainly not classified. It's impossible to classify because you cannot even classify Lie groups, right? So Lie groups are special cases of homogeneous spaces. So so there's a lot of geometric properties. As far as we're concerned, we don't know the answer. Here, let me just give a specific example to illustrate what I mean. For instance, there is a special type of homogeneous space we call Kähler-C space. So these are fully classified. Kähler's, in algebraic geometry, they call it flag manifold, right? Flag variety. On this Kähler-C space, there's a canonical Kähler-Einstein matrix. And they are various, but if you ask the question of whether this canonical Kähler-Einstein matrix have positive holomorphic sectional curvature or not, it is still an open problem. So even for Kähler-C space, which is fully classified, we don't know if they all have, if the canonical Kähler-Einstein matrix all have positive holomorphic sectional curvature or not, even though it's widely believed so. But I think the best result in that regard is when the second Betti number for the irreducible ones, when the second Betti number is less than or equal to 5, then it's true. But for general, B2 can be anything, right? So it's still not well understood. So now let's switch to the complex case because I'm primarily interested in complex manifold. So on a complex manifold, we consider Hermitian matrix, which means Riemannian matrix that are respected J, the almost complex structure. I mean, this is there's no obstruction to that. So if you start with any Riemannian matrix H, if H doesn't respect J, you just take the arithmetic average of H with the pullback of H, then it's Hermitian. So on any complex manifold, you always have Hermitian matrix. Given a Hermitian matrix, then of course we could consider a Levi-Civita connection. But the problem is that the Levi-Civita connection may not respect the almost complex structure. So if it does, then we call the matrix Kähler, right? So Kähler geometry is well studied and in some sense well understood. But if the matrix is non-Kähler, then this Riemannian connection is not the best connection to use because it doesn't respect J, so it doesn't preserve the PQ type, so all you do is Riemannian geometry. It's not clear in the end how that is related to the complex analytic property you're trying to understand, right? So instead we use some other connections. So the Chern connection is one that is widely used. So this is a connection that we call Nabla-C, right? So first of all, it's a metric connection. So and it preserves the almost complex structure. So both G and J are preserved. So this kind of connection we call a Hermitian connection, right? But Hermitian connection still forms an infinite dimensional affine space. So it's still too many. So you have to, if you want to specialized to one, then you have to put some restriction on the torsion. So if you require the torsion, which we denote by TC, if you require TC to be only containing the 2-0 part, no 1-1 part, so that's the condition when you write it out, it's this equation. And then it's then that will make it unique, exist and unique. So this connection is called Chern connection. And it exists not only on the tangent bundle, but also on any holomorphic vector bundle. So because it can be equivalently characterized as a metric connection that whose 0-1 part is the partial bar. So any holomorphic vector bundle will have, I mean, when you equip it with a Hermitian metric, will have this unique connection. So that's the connection that is most widely used in algebraic geometry. So besides this connection, there's also this Bismuth-Strominger connection, which requires the torsion to be totally skew symmetric. So the torsion, when you use the metric to put it down, it becomes a 3-0 tensor. For the first two variables, it's obviously skew symmetric by definition. But if it is also skew symmetric with respect to the last two position, then it becomes a 3-form, right? So this is the exist and unique. So it's called Bismuth connection. And also you can connect the Chern and Bismuth by a line. You join them by a line. So this is usually called T-Gardouchon connection. So Paul Gardouchon was the first one to use it. So this is a one-parameter family, right? And of course, you could also so this is called the Gardouchon line. The Levi-Civita connection is away from the Gardouchon line. So if you use the Levi-Civita connection and Gardouchon connection, it spans a plane, right? So this is called the canonical plane of metric connections. So when the metric is scalar, all these connections coincide. So there's just one geometry, right? But when the metric is non-scalar, then any two different pair in this plane will be distinct. So in other words, any two connection equal means is equivalent to the scalarness. So non-scalar geometry, you have at least three kinds of geometry, right? Riemannian geometry, you have Chern geometry, you have Bismuth geometry. So now let's come back to the homogeneous space. So first of all, for the symmetric space, so we call it a Hermitian symmetric space. So this morning, Professor Mock was talking about bounded symmetric domain, right? So these are examples of Hermitian symmetric spaces. They're fully classified. So besides the flat one, the Euclidean space, then there are compact ones and non-compact ones. They're in duality, right? The non-compact ones are exactly the bounded symmetric domains that Professor Mock was discussing this morning. So these are called classical domains, right? Bounded symmetric domains. There are 4 classical sequences plus 2 exceptional ones. So they can be written down explicitly, right? So it's just these are bounded symmetric domains. For example, type 1, that include the ball, right? Ball is a special case when when m is equal to 1, for instance. Professor Hua has this monograph in the 1960s, which is a classical reference. Now, for homogeneous space, it's the same. We assume we have a Hermitian manifold. So Hermitian manifold are special Riemannian manifold, right? So when it's homogeneous as a Riemannian manifold, then we call it homogeneous Hermitian manifold. In other words, the group of holomorphic isometries were acting transitively, right? So here, I guess there are some pioneer, old classic work is by Xianzong Wang and by Tietz, right? So these are and others. So for homogeneous spaces, there is a complex analog Hermitian version of Ambrose-Singer theorem. So this is done by the Japanese mathematician Sekigawa in the 1970s. So the statement is exactly what you expected. Namely, if you have a complete, simply connected Hermitian manifold. So how do you know it's a homogeneous one? Well, that will be the case if and only if there is a Hermitian connection, which is Ambrose-Singer. Okay, so the problem is that this connection might not be unique, so that will add the technical difficulty. So so here we ask a very naive question. So namely, for Hermitian manifold, if you have a Ambrose-Singer connection, the Hermitian Ambrose-Singer connection, then it's homogeneous, right? But then on a Hermitian manifold, there are some canonical connections, for example, Chern connection. So we can ask the following question: when will the Chern connection be Ambrose-Singer? So this is stronger than saying being homogeneous, right? So for that reason, we call it Chern homogeneous. That's why in the title of the talk, we see the term Chern homogeneous. So it is homogeneous for sure, but it's stronger than that. We wanted the specific Chern connection to have parallel torsion and curvature, right? So of course you can replace the Chern connection by the Bismuth connection, or more generally by the Gauduchon connection. So you can introduce this Bismuth Ambrose-Singer, right? So we call it BAS. See, the name is too long, so we use the abbreviation. So in the second part, so we would like to discuss the CAS. CAS means Chern connection is Ambrose-Singer. So first of all, let's see some examples. So of course, if the matrix is scalar, then this condition, this Ambrose-Singer condition, simply means the curvature is parallel, which means locally symmetric, right? So Hermitian symmetric space, all their compact quotients are obviously CAS, right? So that's the Kähler case, that's a trivial case. And then if the manifold is Chern flat, namely if the Chern connection, if the curvature of Chern connection is 0 everywhere, then it's a classic theorem of Boothby, which shows that if you assume the manifold to be compact, then there is a Bachner technique that will ensure the torsion to be parallel. So initially you only require the curvature to be 0, right? But because of compactness, in a non-compact this is not true. But in a compact case, the torsion will have to be parallel. So this is proved by Boothby. And not only that, the universal cover has to be a complex Lie group. So in other words, compact quotients of complex Lie groups are all these compact Chern flat manifolds. And these are CAS, because in this case, both torsion and curvature are parallel, right? So these two examples are the obvious examples. In some sense, they're the trivial examples, right? So the question now becomes, are there any non-trivial examples? So that's really the question. So here, I give an explicit example. This is a famous Iwasawa manifold. Namely, you consider the C3, but with a non-abelian group structure, right? Consider all these upper triangular matrix with one on a diagonal line. So this is really C3, right? But the group structure is different. So then you consider these three holomorphic one forms, namely dx, dz, and dy minus x dz. So these three are left invariant, right? So they descend to downstairs. So the downstairs, when you mod out by all these Gaussian integers, then become a compact complex manifold. So this is Chern flat, right? So it's non-Kähler. So starting in dimension 3, so these Chern flat manifolds can be most of them are non-Kähler. So if you take the product of Hermitian symmetric space with complex Lie groups, so these are the trivial examples. The question I mentioned is, are there any other examples? So the result of our study is that there's no other examples. So this is a rigidity result, right? So namely, cast manifolds, their universal cover must be either Kähler or Chern flat. So we actually wrote 2 papers on this. In 2023, we weren't able to prove the theorem. We were only able to prove it in that complex dimension less than or equal to 4. The reason is that the proof consists of 3 parts, and so at that time we couldn't handle the 3rd part. So that's why we can only do by brute force the low dimensional case. So the first part is to extract the Kähler-Durham factors. The Kähler-Durham factors essentially comes from the kernel of the torsion. So so that part we know how to. I mean, this is kind of standard argument. So this can be done. The second part is to show that if you exclude these Kähler-Durham factors, these non-Kähler-Durham factors, they're always Ricci flat. So this is achieved by using the torsion and curvature conditions that we have to construct a holomorphic symplectic form. So this is a parallel holomorphic 2 form that is non-degenerate everywhere. So as a result, the Ricci curvature will have to vanish. The third part is to go from Ricci flat to flat. So this is usually called in the literature an AK type theorem. So we were able to achieve this by proving an algebraic analog, generalizing Simon's holonomy system. So in the 1960s, Jim Simons gave a proof of Berger's holonomy theorem, gave a purely intrinsic algebraic proof, abstract proof. So, but in his case, his holonomy system is for the Levi-Civita connection, so it's torsion free. Here we basically need a Simon's theorem for the connection with torsion. So you need to expand the system a little bit. So that's the essential. So let's recall the so here I explained this AK, right? These 2 Russian mathematicians in the mid 1970s, they proved a surprising result. Namely, if you only consider homogeneous space, then Ricci flat means flat. In other words, any homogeneous space that is Ricci flat is actually flat, Euclidean space. So here, let me give a remark. So this is, you notice the year, this is right before Professor Yao's proof of Calabi conjecture. So back then, there's no single example of a compact Ricci flat manifold that is not other than flat manifold. So there's not a single example. So someone told me there was even a conjecture that any Ricci flat manifold must be flat. Of course, Yao's solution to Calabi conjecture shows that there's lots of all these Calabi-Yau manifolds, right? They're Ricci flat, but not flat. So now we know there's lots of such examples. But back then, so this also show the significance of course. So as a consequence to our rigidity result we mentioned earlier, so we could say that for Chern connection, the AK type theorem is valid. Namely, for cast manifold, Ricci flat means flat because the for Hermitian symmetric space, if it's Ricci flat, it must be flat, right? So the Chern flat part is already flat. So there's so this is a trivial consequence. Okay, so that's the story of a Chern Ambrose Singer case. And I didn't go into detail of the proof, but I gave you the outline of our the 3 steps of our proof. So now, if you replace the Chern connection by Bismuth connection, then the situation is a little bit different. So So first of all, we also have Hermitian symmetric space. That's also Bass, right? That's the Kähler case. And then the Bismuth flat manifolds, they are also examples of Bass, right? If the Bismuth curvature is identically 0. So so these are the so-called Samuelson spaces. So namely, if you start with a compact Lie group, even dimensional compact Lie group, or more generally, a Lie group with a bi-invariant matrix, right? So by Milnor's lemma, so such Lie groups must be a compact semi-simple Lie group times a vector group, right? You could have a vector. So now, on such Lie group, there is essentially a unique way to equip it with a left invariant complex structure. So that goes with the root system, right? And on the torus part, you do have arbitrariness. So if you have a Lie group equipped with a bi-invariant matrix and a compatible left invariant complex structure, it becomes a Hermitian manifold, right? So this Hermitian manifold is known to be Bismuth flat. So this is proved by Indian mathematician Petit in the 1980s. But I assume experts before him might know that already. But they probably don't have the concept yet. So okay, so we so in some literature it's also called Straminger connection. Yeah, his paper was in 1986, prior to a Bismuth paper, but that's in physics, so a lot of mathematicians don't know that. So in the math literature, they're yeah, right. So in a joint work with my student Wang and Bo Yang from Xiamen University in 2020, we were able to prove again, it's a rigidity result. Namely, if you have a compact Bismuth flat manifold, then it's just this quotient of Samuelson space. There's no other examples. So so kind of like Busby's theorem. So unlike the Chern case, so besides these trivial examples, there are actually non-trivial examples. So for instance, here we can give an explicit example. Namely, you consider the standard Hopf manifold. Here you take the punctured complex Euclidean space modeled out by this holomorphic contraction, right? And then use the standard conformal Euclidean matrix. Then you can check. This is actually Bass. You can check. But for dimension 2, it is also Bismuth flat. But for starting in dimension 3, it's not Bismuth flat. And obviously it's non-Kähler. So this gives a non-trivial example of Bass. So there are actually other examples as well. So so this Bass category forms a subset of the so-called naturally reductive homogeneous space, which is a very special type of homogeneous space. And people, there's a whole bunch of people studying NRHS, and they try to classify it. But so far, I think they were only able to do it in dimension up to dimension 8, real dimension 8, because when you increase the dimension by 1, then there's a whole lot more. So there's a lot more examples every time when you jump by a dimension. So our goal is to somehow classify Bass. We believe there's not much hope for NRHS in general dimension. At least, well, maybe you have a very coarse classification. If you have a classification in the usual sense, namely giving a list, it's probably impossible. But for Bass, it's a much smaller class. So we think there might be a good chance to classify them. Of course, for Bass, we have this added difficulty, namely when people are doing this real homogeneous space, they don't care about complex structure, right? But here we have complex structure that you have to discuss, because on the same real homogeneous space, there might be more than one homogeneous complex structure fit with it, right? Yeah, so this is what I just said. So of course, classification might be a long-term goal, and the easier target would be asking a AK type question, namely, if this connection this spatial metric connection, if it's Ricci flat, must it be flat under some assumption? Here, our assumption is Bass, right? So in the Bass case, if it's Ricci flat, must it be flat? So that's our conjecture. So we asked a slightly weaker, we stated a slightly weaker statement, namely, we require all the Ricci curvature to vanish. You see, for this type of metric, there are 3 Riccis, right? So the first 2 Ricci are always equal because of the Bass condition. So here we basically just require all 3 Ricci to vanish, and then we ask whether it's flat or not, right? So and even for this weak statement, we couldn't do. We only right now we were only able to do in this paper we were only able to do it for dimension up to dimension 4. So for general dimension, we were able to show that it is non-balanced, because if it's bismuth flat, it's always non-balanced. So in a way, we were able to prove this necessary condition, but it's far away from showing flatness. So the reason is that in the Chern connection case, if you consider Cass manifold, and then the behavior of the curvatures is very nice. So they're so-called Killer-like. So under the Cass assumption, the curvature of the Chern connection obeys all these Killer symmetries. So they behave like the curvature of a Killer matrix. But in the Bass case, you only get partial symmetry. Some of the symmetry conditions are satisfied, but not all of them. In the Killer case, you can switch the first and third position, right? But in the Bass case, you weren't able to do that. But you can switch first 2 with the last 2. Okay, so you get sort of half of the symmetry. So that's why we want the first and third Ricci to both vanish. I think the stronger form would be just assume the third Ricci to vanish. Third Ricci is the usual Ricci, right? So at this point, we don't know if the third Ricci will imply the flatness of third Ricci will imply the flatness of the curvature. And since I still have a few minutes, let me also mention the Gauduchon case. So the Gauduchon case, so here we normally require this parameter t to be other than 0 and 1, because those 2 corresponds to Chern and Bismuth case. So we want to exclude those 2. And then of course, you can ask, do you have examples of T-gas manifold? There are actually non-trivial examples as well. But these Gauduchon connections tend to be more rigid. For example, this is a very nice theorem proved by Lafontaine and Stanfield. They show that if you have a compact Hermitian manifold, if its Gauduchon connection is flat, then it must be torus, complex torus, must be Killer. So in other words, you don't have any non-trivial flat case like the Chern or Bismuth case. So Bo Yang and I, and also we were able to prove some partial results. The thing is, with this theorem, the hardest thing to do is when t belongs to a critical interval. So beyond that interval, there are previous works, and also a more general result by Professor Fu and Zhou Xiancao. So they were also able to prove a partial result, excluding that. But they were doing it for almost complex case. So that's a broader category. So but these T-gas examples are extremely rare. Here, let me give an explicit example. So if you consider the only three-dimensional simple complex Lie group, so this is so-called SL2C, right? So you take any compact quotient of it. So this becomes a compact Hermitian manifold that is Chern flat. But it turns out that this manifold is T-gas for all T. It's non-killer, right? So and it's not Gaussian flat or Bismuth flat. So these are non-trivial examples. So but these, like I said, these examples tend to be highly restrictive. So it will be a nice project to try to classify them. So for T-gas manifold, we were able to prove a property, a partial property, namely for general Gaussian connection. So if you have a T-gas manifold, then it must be balanced. So balance means the Kähler form is co-closed. So this is a extensively studied special type of Hermitian manifold, and if it has vanishing first and third Ricci, then it must be flat, hence Kähler, right? So we were able to prove this sort of weak form of AK theorem, but classification we're not able to do. Okay, I'll stop here. Okay, thank you.
Thanks for the next talk. Okay. So are there any questions or comments?
Compact dimension 4, why is it the most case the technical difficulty at complex?
Oh, because we weren't able to handle the general dimension case, so we just do it by brute force. And in dimension 3, we have Chuan-Ting Zhao and I did some. We have a classification theorem. Essentially, we have a good understanding of the threefolds. So dimension 4 is sometimes you have an extra dimension to work with, so you can do one more. But so that's, I think the three-dimensional classification paper was the key reason why we can do the low-dimensional case. Yeah. So for this type of question, dimension 2 is usually very easy because you have a classification theorem for compact complex surfaces. So essentially, you know what kind of objects you have. But starting in dimension 3, you have no idea how many non-Kähler manifolds are there, right? But since we're adding these very restrictive conditions, so in dimension 3 we have some partial classification. So yeah, so you mean just the connection. You want the connection to be torsion free? Okay, that homogeneous, yeah. So Professor Yao has a famous, well, I shouldn't say famous, has a old conjecture. I don't know if you still will stand by it. In the 1980s, when I was a student, you give us a question, namely, if you have a compact complex manifold, if there's a Hermitian connection that is flat, no major, not Hermitian, just yeah, a Hermitian compact Hermitian manifold with a flat connection, flat Hermitian connection. Then what can you say? I think Professor Yao's projection was it's a Lie group, quotient of a Lie group, but I think it's still open. The problem is that well, the Hermitian connection, as I mentioned earlier, form an infinite dimensional space. Hermitian connection just means compatible with metric and almost complex structure, right? So they form an infinite dimensional space. So the property of, you just assume the curvature of this connection is 0. But if you write down it as a PDE, then it's you have no idea how far this connection is from the Levi-Civita connection. So there's no explicit path. So the flatness of a curvature doesn't give you any control about its torsion. Torsion is essentially the distance from the connection to the Levi-Civita connection, right? So you have no control on the torsion. So that's why this conjecture is still wide open. I've been interested, but sorry that I wasn't able to. But Chern connection or Bismuth-Stramier connection are different. They're explicit, in some sense, right? So that's if you Professor Yao is interested in abstract connection, that's very difficult. I have no clue.
Any flow-based approach to
Yeah, some people are doing this so-called Hermitian curvature flow, right? Basically, it's kind of Ricci flow, but I use second Ricci instead of usually the third Ricci. There are some, especially for pluriclosed metric. So this pluriclosed flow, I think there's lots of interest. But for this type of question, I think we haven't seen any parabolic sort of approach yet. Yeah, but it's an obvious path. But I guess the estimate must be hard because of the presence of the torsion.
So there are some recent results by Barbaro and Nicolette Tardini, also Fino Granchero.
But they have a brand new paper on BAS, right?
Yeah. So my question is, I think the only condition that they impose is that the torsion of the Bismuth connection is parallel, but they get very rigid results. So how does this compare to yours?
Are you talking about their most recent preprint on arXiv?
Last year there was one by Barbaro. And
last year, well, the thing is, for their most recent paper, I didn't mention their work because their work is too recent. They were able to give a partial result to the classification of all BAS manifold, but the condition they assume, if I'm not remember wrong, is that they assume simply connected.
Okay.
So compact and simply connected, that's a very strong assumption. Because essentially your homogeneity is on the downstairs. So that's a very strong assumption. But even in that case, I think it's a very nice result. Yeah.
Thank you.
Yeah.
Any further questions? Okay. If no, let's thank Professor Zhang again. Okay.
Thank you.
Hello, Professor. Can you hear us? Professor Wiener?
Are you talking to me?
Yeah. You can try to share your screen.
Yeah, we do. You must see it.
So you use Blackboard, right? If you use Blackboard,
I use Blackboard. Yes.
No problem. We can see.
Yes. Okay, so when should I start?
Yeah. Okay, no problem. So we will start 2 minutes later.
Okay.
没事，您还用这个，这个是我用的。
Oui? In Tsinghua University.
In Beijing.
Wie?
Da bin ich im August.
Ja. Da ist mein Vortrag aber zu Ende.
Ja.
Ich muss danach zu meinen Enkeln. Also ich bin ganz am Schluss etwas unter Druck.
Was ich das zu Ende geht.
这个就特殊了，它是因为写黑板，所以咱们录的时候把这个去呢录全屏了。这个哦，咱得调一下那个，就直接把它全屏了，不用标准回去。对，然后全屏在这里。这标准。对，来。啊。啊，我懂了。啊，对，应该是。
他那个，
啊，
他那个上面那个框又出来了，你给他
点进去，点就行。
点了，
有一个隐藏，那不是说没在是吗？
哎，对，
去哪儿了？
就点那个框就隐藏吗？
没事，你先让那个。因为添加话筒。那个是听了吗？我理解是到一个更好的概念。
我还得裁剪一下那个。
Okay. Our second speaker is Professor Werner Bormann, and the topic is spectral stability and instability of finite Manning couplings. Okay, let's welcome.
Yeah, thank you very much for the invitation on introduction. Pardon?
Ist gerade nicht, gerade.
Okay, you have a problem there?
Ja, wir haben ein Problem. 我裁一下，因为我是给他取。
Can I start?
Yes.
So we let M. Oh, I have to put this on. You let M be a Riemannian manifold.
我可以拉伸，不是拉伸，不用拉伸。
And there I have to introduce some notions before I can state the results. So lambda naught of M is the bottom of the spectrum. So really of the Laplacian of M. When I speak of the spectrum of M, I mean the Laplacian. And lambda S of M, the bottom of the essential spectrum. Of M. So then below lambda S of M, below so the essential spectrum consists of points lambda, where delta minus lambda is not a Fredholm operator. So and the bottom below lambda S of M, the spectrum is discrete. This is a discrete subset of R. And consists of eigenvalues of Laplacian of finite multiplicity. And if M is compact, then we have the the essential spectrum is empty, then lambda s of m is equal to infinity. And for example, if m, the volume of m is less than infinity, then lambda 0 of m is equal to 0, and it is an eigenvalue of multiplicity 1 in general. Not all, in this case, it's an eigenvalue of multiplicity 1, the constant function being the eigenfunction. And then we have lambda 0 of m is less than or equal to lambda 1 of m, and we count eigenvalues with multiplicity as long as we below lambda essential of m. So actually there might be no eigenvalue, but if lambda 0 of m is less than lambda s of m, we count these eigenvalues in between. There might be none except for lambda 0, according to the usual rules. Yeah. Okay, these are the general kind of notions. Now let's consider the finite Riemannian cover. I should say all my Riemannian manifolds are assumed to be complete and connected, so don't worry about connected components or whatever. Then we have the bottom of the spectrum of m prime is equal to the bottom of the spectrum of m, and also the essential spectrum, like from the bottom of that. And for lambda less than the essential spectrum, we say that P, this finite covering, is lambda stable if the number of eigenvalues of m below lambda. So nm of lambda denotes the number of eigenvalues up to lambda and including lambda. It's the same, maybe to do it the other way around. Nm prime of lambda is nm of lambda. You see, in general, we have pullback P star f of an eigenfunction f on m is an eigenfunction on m prime. And including square integrability, because we have a finite Riemannian covering. So square integrability doesn't change. And so then we say that so you see that always, we always have this because you can pull back and get eigenfunctions on m prime. And the question is whether we have inequality or not. That would be instability. If that would mean we have new eigenfunctions on M prime which do not come from M. So I will speak of new eigenfunctions and also of old eigenfunctions. And the new eigenfunctions, we can assume that they are perpendicular to the pullback, because I mean we have this the self-adjoint operator. We can split the spectrum orthogonally into eigenfunctions below lambda essential of F. And there's an observation maybe made by many people, I don't know, but we have it in a survey paper, Mathieson, Mondal, and I, in a survey paper on the notices of the ICCM. So there's the observation. If S is a surface of genus G greater or equal to 1, so the standard one, oriented and compact, G a Riemannian metric on S, for example, a hyperbolic one, if G is greater or equal to 2, and C is non-separating or closed curve on S. Okay, I don't need this for this non-separating curve. I don't need for the statement. Then for any n and epsilon greater than 0, there's a finite Riemannian covering S prime to S of degree P greater or equal to n, such that sorry. So the degree will be denoted by absolute value of P, and I'm covering with n S prime of epsilon is bigger than n. So it's a compact surface, so the spectrum is discrete for all of R, and you have this counting function up to infinity. And what I'm saying is you have as many eigenvalues below epsilon as you wish, bigger than n, if you choose S prime correspondingly. So what you do is you have this Riemannian metric. Then the free homotopy class of C contains a closed geodesic without self-intersection. You cut the surface along that closed geodesic, and then you glue pieces of what you have if you cut it open, construct a Riemannian covering, and test functions which allow you to get n functions on this covering which are pairwise orthogonal and have small Rayleigh quotient. That's an easy construction. I don't go into details because I don't have much time. So we have this result, well, we have this observation. And now we were very surprised when we learned about the result of McGee and Hyde and McGee. So that's in the annals from 23. Actually, I think we saw it in the archive before. I don't remember, it's a long time ago for me. So it says the following. Let S be hyperbolic. Hyperbolic means curvature equal to -1. A hyperbolic surface, be a hyperbolic surface, non-compact, finite area, then the proportion and let epsilon greater 0. Or let lambda less than 1/4. You know the number of 4 occurs always if you discuss hyperbolic surfaces. Let lambda less than, then the number, the proportion of lambda stable coverings, so let me just so the proportion of lambda stable. So up to lambda, you have as many eigenvalues, only as many as you have below. You have no new eigenvalues below lambda, and also lambda. Of lambda stable, finite remaining coverings. I don't write this. Then the proportion tends to 1. As n tends to infinity. As the by n I mean the 5th degree. Maybe I put an n here. It's a different n, not the same meaning as that one. So on the one hand, in this observation, and I don't tell all the arguments. It's not difficult. In the observation says it's very easy to construct unstable remaining coverings of such a surface, because we have such. Yeah, here it's only for compact surface, but it's also the same argument works for these surfaces. But on the other hand, what they say is there are many stable ones, which is kind of not in contradiction, but it certainly is in contrast to this observation. When Mondal talked to me about this result, we were really couldn't believe it even. Yeah, so it's kind of, yeah. So let me just clean more blackboards. There's something else related to the 1/4 here. Let me quote a result which Mondal and I proved at about, I guess, the same time, which is related to the 1/4. It's also an easy theorem. So B refers to Ballmann and M refers to Mondal. Yeah, so that's easy enough. So let P tilde M with the universal covering. And so we assume that lambda is a number between these two numbers. We take the essential spectrum of M tilde. Here, the the usual universal covering is the hyperbolic plane of curvature -1. And the number here is just this 1/4 here. This number, so. And let so it's this inequality is important. And then there exist n in n such that for any finite remaining covering of M, finite remaining with T greater or equal to n, we have lambda L is bigger than n, bigger or equal, well, bigger than n. So beyond 1/4, in this case, you have a hyperbolic surface. Beyond this 1/4, which is lambda, the essential spectrum. Beyond that, you can produce as many eigenvalues as you like by passing to a sufficiently high remaining covering. So you cannot expect stability beyond this. So they are below this and show stability below. I mean, in probability, they say in proportion, so to speak, then the proportion tends to 1. Okay, so maybe here. So then, yeah. So this is kind of not in contrast to that one because it is above the essential spectrum. By the way, and in this case, the essential spectrum, in the case of Hyde and McGee, the essential spectrum of the surface itself, because of the ends, we assume non-compact, you have these cusps at ends, is also 1/4. Okay, so we started to discuss this and studied the paper of Hyde and McGee. And yeah, so the proof of Hyde and McGee, and yeah, that's always a matter of taste, can be separated into 2 parts. One is algebraic topological and discusses coverings and a certain description of coverings. And it is important that the in the proof that the fundamental group of the surface is free. That's a very specific property of these surfaces. And the proof would go through if the fundamental group has a certain property which free groups have. And this property refers to representation theory of the group. I may have time to come to that a little bit, but let's see. But anyway, so the other part is geometric, and the geometric part, let me talk a little bit about the geometric part. So let me call it structure of proof, or maybe so we were kind of, so that, as I said, we have this algebraic geometric part and the algebraic topological part and the geometric part. And we were able to generalize the geometric part of the proof. And so let me and the geometric one. And so we were able to generalize this geometric part and still use the algebraic topological part in our situation. So we had to reformulate things and so on. But so we have the following theorem. So this is again me. Now by alphabet, that's because I'm B. This is first place. So that's, we proved this in 25. So let me see. Not to make it, I think I have it in mind, but let M be remaining manifold, complete and connected. And what we need as assumption is that the Ricci curvature is the Ricci curvature, no, the Ricci is bounded from below. And then suppose that the fundamental group by 1 of M is free. And let lambda be a number which is less than the minimum of the essential spectrum of M, and lambda 0 of M tilde. I will say something about this. These are two different assumptions which refer to two different parts of our proof. Then, among all finite Riemannian covers, the proportion of lambda, oops, we have lambda here, lambda stable ones tends to 1 as the degree tends to infinity. So that's the same result as Heiden-McGee, but the generality is different, and that's because we have different arguments in the geometric part of the proof. It's so let me talk a little bit about the proof of this. So first of all, this last conclusion is related to fundamental group being free, but that's as was proved later, the relevant condition which we need here is also true for compact hyperbolic surfaces, for example. And so this is the same statement is also true in that case. We formulate in the paper, we formulate a general property for the fundamental group. If that property is satisfied, then we have the conclusion of that theorem. And but of course also here one has higher dimensional examples, not only surfaces where this applies. Okay, so the proof. So there are two main tools which make our arguments work. And the first one is the Cheng-Yao inequality. So the gradient estimate which is from Cheng-Yao, this is from 75. It's a classical result. The second one is new and concerns concerns construction of test function or cutoff function. Actually, we use a formulation which you find in a paper of Jiang and Neighbor. But this it really is this older thing. Golding, that's in 1996. So also already quite old. These are the two main tools, or two main tools in our construction, which we use in our construction. And both of them require that the Ricci curvature is bounded from below. And these tools are responsible for the assumption bounded from below in our discussion. And what do we do in this in the proof? So what we do is we construct a parametrics for so we have the P kappa, let's call it P kappa for delta prime minus lambda minus kappa on the orthogonal complement of the pullback functions. Let's call that nu. So those functions which are perpendicular so you take B star of L2 of M perpendicular. And the other ones, this one would be called the old ones, yeah. So we can construct the parametrics such that I have to, I guess, have a look at the time. So that we have we want an inequality for this. So you take delta prime minus kappa, and the parametrics is not an inverse. That would of course also be parametrics. Is equal to the identity plus, and then there is some rest. And the rest has operator norm less than 1. And that's what you have to work on. So to have to estimate what you in your construction, what is the rest? How can you estimate the rest? And the important point for the proof is that the rest has norm less than 1, which means that delta prime minus kappa must be injective, because this map on the right is injective. So this one has to be injective, which means that kappa is not an eigenvalue. And because we are below the essential spectrum, it's the only thing which can occur in the spectrum. You only can have eigenvalues, so you have stability. So this is on the perpendicular, on the perpendicular part of the pullback. And so then the question is, how do we get at this perpendicular part of the pullback? And let me just shortly describe this. So we have this finite covering, any finite covering. So then above each point, you have the sheets. So here we are in the base. Here we are in M prime. And you think of the sheets as parallel sections of a flat Hermitian vector bundle. I think you can do this. I mean, you can just think of it that way. What happens? Yeah, you think that's maybe you can numerate them. That's your frame, first frame vector. Let's call it F1, F2, F3, and so on. So of course you don't have that globally. So globally you have the holonomy coming in. Well, for the vector bundle, but here for the covering also. What do you have globally? So if you have a loop at your base point X, you can lift it. You take a point in the fiber over X of the covering, and then you lift your loop. You get another point in the pre-image. So that's a covering. That's a That's an action from the right of the fundamental group on the fiber. Now, in the view of flat Hermitian vector bundle, it's exactly, if you view the sheets as elements of a frame, it's exactly how the frame closes up again by the holonomy. So the right action of the fundamental group on the fiber over a given X corresponds to the holonomy of the vector bundle in that point. And from that point of view, what is a function on M prime? A function on M prime is just a linear combination Fi but that corresponds to such. So a function f on M prime corresponds to such a linear combination. But observe, these functions are smooth functions on M, not on M prime. And they of course they behave, they change under the holonomy as required. So they are not globally defined, but they are globally up to holonomy. And what are the pullback functions? The pullback functions are those functions we have a pullback if and only if all these functions coincide. Because, I mean, if you have a function here, you pull it back, the value at the different points of the fiber is always the same. So, yeah. Now the holonomy in this case, what is the holonomy? The holonomy, so the holonomy of a flat Hermitian vector bundle is a homomorphism from the fundamental group to the unitary group. But in this case, we have more information. The holonomy only interchanges the leaves of the covering, which is our frame. So the holonomy fibers are factors over the symmetric group Sn, where n is the number of sheets when you numerate the leaves. And so what we have is the holonomy is of the form rho n composed with some representation, some homomorphism of the fundamental group, let's call it gamma, the fundamental group at that X, into Sn. So that's our description of these coverings of degree n. You take an arbitrary phi in whom gamma Sn, and then you take the standard representation. Rho n is a standard representation of what? Of Sn on the set of n elements. So that's what we have. And now we have to bring in this pullback. So the pullback consists of functions. So rho n goes to the unitary group in Cn, the standard representation, but actually the perpendicular, but rho n 0 is the restriction. You restrict it to Cn 0. So the standard representation on un has an invariant vector, namely the vector with all entries equal to 1 of rho n, yeah. Rho n is the permutation group. And so it leaves that vector invariant, and it's linear. It's linear span as well. And perpendicular to that, you have functions which are perpendicular to the pullback functions. So that's how we catch this perpendicular space. And then we have to discuss estimates for this. And what we do is the essential, let me just finish with with a few words, it's almost over. So what we do is the bottom of the essential spectrum can be described as the limit of the Dirichlet spectrum, for example, of the complement of smooth domains in M. So if you are below the essential spectrum, that's where this assumption that lambda is less than the essential spectrum of M. If you are below that essential spectrum, if you take your domain sufficiently large, then you are above lambda with the Dirichlet eigenvalues or Dirichlet spectrum of the complement. So that's where this assumption comes in. So if M is compact, it doesn't play a role, of course, because of this infinity there. So that's how this first estimate comes in. The second estimate comes in. Then if we are below lambda 0 of M tilde, you have the resolvent below that lambda 0 of M tilde for delta minus lambda on the universal covering. Then you use this Giga-Kolding cutoff function to cut off the resolvent. It's given by a kernel and make it invariant. And the Cheng-Yao inequality is used to control what you get in this way. Okay, I think I stop here.
Okay, thanks for the next talk. Okay, so now it's time for questions or comments.
Maybe I answer the question.
Thanks for the nice talk. I'm just curious. So could you briefly explain how the fundamental group being free plays a role in the proof?
It plays a role in a property of free groups. There's an inequality. So you have a finitely supported map from gamma let me see. Yeah, there's an inequality which I should have. You have a finitely supported map to the matrices of size R, where R is some number greater or equal to 1. And you have a phi from gamma to the symmetric group Sn. So this R and this N are not related. R is much bigger. It's some big number. And later on, we have this property so then you have the following inequality. A of gamma, I did not like this. Your summation is over gamma. Tensor rho N0, that's our restriction to the orthogonal complement of this simple vector, 1, 0, composed with phi, gamma. You take the operator norm of that is less than or equal to so rho infinity is the right regular representation of gamma on L2 of gamma. So you could consider this inequality. And then there's a famous of Bordenave and Collins, which says that for the free group, as n goes to infinity, this holds almost surely for a given representation phi. So that's a result from random matrix theory. And the same kind of, so that's from, let me see, that's from, I think from, it also appeared in the Annals. I don't, yeah, I find it. Annals 19. So they proved it for holds for free groups. Oh, okay. Maybe the statement is so for the proportion of phi among all homomorphisms which satisfy this inequality for the given A. It's a finitely support map. The proportion of phi tends to 1 as n tends to infinity. So that's a deep result from random matrix theory. And the analogous result for gamma, the fundamental group of a closed surface of genus greater or equal to 2, was proved later by, well, McGee, McGee disappeared, McGee, Pudor, and Van Handel. So there's a later paper. I don't think it appeared. I didn't find it in MathSciNet, but you find it in the archive.
I see. I see. And the inequality here you used is like to prove or to construct the parametrics like satisfying this L of
gamma. Yeah. So in the end, this will help to estimate one of the terms which you have. So you can estimate the other terms separately. They are easier, but the main term is estimated by this inequality. This inequality goes into the estimate.
I see. Okay. Thank you.
Okay. Okay. Let's thank Professor Borman again. Okay.
Yeah. Thank you.
Okay.
And bye. Sorry, I don't know how to. Wir können die Woche drüber sprechen.
1、2、3、4、5、6、7、7、6、5、4、3、2、1。
Okay. Our third speaker is Professor Ji Xiangfu from Fudan University, and the talk title is the critical LYZ equation. Okay, let's welcome.
Thanks for the introduction. Today I talk about the critical pairwise equation. It is a fully nonlinear equation in Kerr geometry that arises from Miller symmetry and supersymmetric string theory. This talk is based on the joint work with Professor Yao and Professor Dekai Zhang in East China Normal University. Let us begin with some background. At the most fundamental level, Miller symmetry relates complex geometry on one Calabi-Yau manifold to symplectic geometry on another. More precisely, it gives an equivalence between two categories. On the A side, the Fukaya category of Lagrange submanifolds with local systems, and on the B side, the Dirac category of coherent sheaves. In the semi-flat case, Liang, Yao, and Zassler in 2000 derived an equation for connection A on a holomorphic line bundle that corresponds to the special Lagrange equation on the Miller. So this is the equation. The equation for the connection A is this equation. The real part of the NN form, this NN form, omega minus f to the n, which n times equals cotangent theta hat times the imaginary part of the NN form. Here, omega is the Kerr form, Kerr metric. F is the curvature of the connection A, theta hat is a constant phase, and n is the complex dimension of the manifold. This is known in the literature as the deformed Hermitian-Yang-Mills equation, but we call it the pairwise equation after Liang, Yao, and Zassler. The same equation also appears from supersymmetry considerations due to these four physicists, Marino, Minashin, Moore, and Strominger. Now, let X omega be a compact Kerr manifold of complex dimension n, and let chi be a closed real one form on X. The pairwise equation on X, omega, and chi is this equation, the real part of the NN form. Chi U plus the square root of -1 times omega to the n equals cotangent theta hat times the imaginary part of the NN form. Here, chi U equals chi plus the square root of -1 times partial by U for a real smooth function U on X, and the theta hat is the augment of this complex number. This complex number, the integral over X of the NN form, chi plus the square root of -1 times omega to the n, which n times. So this is the NN form on X. So the phase theta hat is fixed by the classes of chi and omega. Now, let lambda1 to lambda n be the eigenvalues of chi U with respect to omega. Define theta I equal to cotangent lambda I, so that lambda I equals cotangent theta I for I from 1 to n. Now we can use these angles to compute as follows. Chi U plus the square root of -1 times omega to the n equals this. So this is the real part of the NN form, and this is the imaginary part of the NN form. So the pairwise equation becomes this equation. Cosine of the sum of theta I from 1 to n equals cotangent theta hat times sine of the sum of theta I from 1 to n, or cotangent of the sum of theta I from 1 to n equals cotangent theta hat, or simply theta omega chi u equals theta 0. If we denote theta omega comes theta omega plus the law of the Lagrange angle. So the LYZ equation is called hypercritical if theta 0 is an actual angle, supercritical if theta 0 is in the open interval from 0 to pi, and critical if theta 0 equals pi. The study of the LYZ equation was initiated by Jacob and Yao in 2014. Now, let me review what is known for the supercritical case, because that will be the foundation for our approach to the critical case. So, for n equal to 2, Jacob and Yao proved that a solution exists if and only if there exists a function u with chi u is bigger than cotangent theta 0 times omega. Denote alpha equals chi u minus cotangent theta 0 times omega. So this is a positive one form and defines a new Cayley metric. Then the LYZ equation transforms into this Complex-Monge-Ampere equation, which was solved by Yao in 1976. For the n bigger than or equal to 3, Collins, Jacob, and Yao solved the LYZ equation for the supercritical case by assuming the following conditions. The first condition says that there exists a subsolution U, which means that chi U satisfies this inequality. The summation over J of the sum over I not equal to J of arctan lambda I chi U is less than theta 0. Theta 0 is less than pi. The second condition says that the function u also satisfies this inequality. Theta omega chi u is less than pi. For convenience, we call the second condition as the extra condition. The definition of subsolutions of fully nonlinear PDE was introduced by Guanbo in 2014. Circulated in 2018 gave an equivalent version of, and Collins Jacob Yao applied Circulated definition to the LYZ equation. To be precise, Collins Jacob and Yao prove this theorem. Let X omega be a compact Cayley manifold of dimension n, and chi cross Leo 1 form on X with theta 0 in the open interval from 0 to pi. Suppose there exists a subsolution of the LYZ equation, which also satisfies the extra condition. Then there exists a unique smooth solution of the LYZ equation. Lin Caoming generalized the Collins-Jacob-Yau's result to the Hermitian case with these conditions: partial bar omega equals 0, and partial bar omega square equals 0. Huang Liding, Zhang Jiaogeng, and Zhang Xi also considered the solution on compact or almost Hermitian manifold for the case theta 0 in the open interval from 0 to half pi. A natural question was whether the condition, the extra condition is actually necessary. Lin Caoming showed that it is superfluous. So this is his theorem. Let X omega be a compact Cayley manifold of dimension n, and chi cross Leo 1 form on X with theta 0 in the open interval from 0 to pi. If there exists a subsolution of the LYZ equation, then there exists a unique smooth solution of the LYZ equation. Previously, this was also solved by Pingali for n equals 3, and by Lin Caoming for n equals 3 and 4. An alternative proof based on Chen Gao's significant result was given by Sun Wei in 2024. For the parabolic flow method, there are also several results. Jacob Yao and Collins Jacob Yao proposed the line bound mean curvature flow. This flow, they call the line bound mean curvature flow. UT partial U partial T equals theta 0 minus theta omega chi U, with the initial data you underline. Here your underline is a subsolution of the LYZ equation. They prove the existence and convergence of the long-term solution to this flow for the case theta 0 and theta omega chi U are the acute angles. Han Xiaoli and Jing Xiseng considered the stability result for this flow. Takahashi introduced the tangent Lagrange flow, phase flow. This flow he called the tangent Lagrange phase flow. UT partial U partial T equals tangent of theta 0 minus theta omega chi U, with the initial data U0. He proved the existence and the convergence of the long-term solution to this flow under the assumptions. These assumptions. The first assumption is that theta 0 is in the open interval from 0 to half pi. And theta omega chi U 0 minus theta 0 is in the open interval minus half pi to half pi. And there exists a subsolution. Motivated by the concavity of cotangent theta omega chi U discovered by Chen Gao, we considered a new flow, this new flow. UT equals cotangent theta omega chi U minus cotangent theta 0, with the initial data U0. Initial data U0 satisfy the extra condition. Theta omega chi U0 is less than pi. We first prove the existence theorem of the long-time solution to our flow. Let X omega be a compact Kähler manifold and chi cross Liu 1 form with theta 0 in the open interval from 0 to pi. If U0 satisfies the inequality, theta omega chi U0 is less than pi. This is the extra condition. Then our flow has a unique smooth long-term solution. We then consider the convergence of the long-term solution. In this case, we should need the subsolution condition. This is our main theorem. Let X omega be a compact Kähler manifold and chi cross Liu 1 form with theta 0 in the open interval from 0 to pi. Suppose that there exists a subsolution of the LYZ equation, which also satisfies the extra condition. Then there exists a long-term solution, UXT, of the flow, with U0 equal to the subsolution, and it converges to a smooth solution U infinite to the LYZ equation. So this is the LYZ equation. Theta omega chi U infinite equals theta 0. Hence, we reprove the Collins-Jacobi-Yau's existence theorem. Our parabolic version seems rather natural and the proof is simpler. In fact, Collins-Jacobi and Yau used a double method of continuity, just as Uhlenbeck and Yau proved the existence of Hermitian-Yang-Mills matrix on stable vector bundles of compact Kähler manifolds. The advantage of our flow is that the imaginary part of the Calabi-Yau functional is constant along the flow, which is the key to do the C0 estimate. We in fact identify which assumption is needed for the long-time existing part and which one is needed for the convergence part. So we can propose the following two questions. The first question is, if theta 0 is in the open interval from 0 to pi, does there exist U smooth function U in on X such that theta omega chi U is less than pi, or how to characterize such chi? The second question is, if U0 is not a subsolution of the LYZ equation, then we can study the convergence and the limiting behavior of long-time solutions. The second motivation is to use our flow to study the equation and the existence of semi-subsolution. This this inequality, semi-satisfies this inequality. We can solve the two-dimension case. In this case, a smooth function U is called a semi-subsolution of the LYZ equation if chi U is bigger than or equal to cotangent theta 0 times omega. We observed that in this case, if there exists a semi-subsolution, then there exists a U0 satisfies the extra condition. We use this U0 as the initial function and then use our flow. So this is the theorem, our theorem. Let X omega be a compact surface and chi cross Liu-1 form. Assume theta 0 is in the open interval from 0 to pi, and chi is bigger than or equal to cotangent theta 0 times omega. Then there exists a finite number of curves EI of negative self-intersection on X such that the solution of the flow with U0 converges to a bounded function U infinite in this functional space. C infinite log of X minus union of Ui as t goes to infinite with the following properties. Firstly, chi plus the square root of -1 times partial by U infinite minus cotangent B1 times omega for some constant B1 is a Kelly current, which is smooth on X minus the union of EI. Secondly, U infinite satisfies the LYZ equation on X minus the union of EI. Thirdly, chi U xt converges to chi U infinite, and U infinite satisfies the LYZ equation on X in the sense of the currents. We notice that by assuming theta 0 is in the open interval from 0 to half pi, Takahashi proved the same convergence result for the line bound mean curvature flow. A similar result for the J flow was obtained by Fang, Lai, Song, and Winkoff in 2014. So one can consider how to solve the LYZ equation and the existence of a semi-subsolution. In this case, the LYZ equation may be degenerate. We hope our flow is useful to solve the higher dimensional case. This is an analogous to the semi-stable case of the Hermitian-Yang-Mills equation. The Hermitian-Yang-Mills flow proposed by Donaldson is very useful in the study of the Hermitian-Yang-Mills equation in the semi-stable case. Now we come to the main part, the critical LYZ equation. We recall the definition, the LYZ equation of the LYZ equation, theta omega chi U equals the sum of cotangent lambda I from 1 to n. And the critical LYZ equation, theta omega chi U equals pi. We recall the definition of theta omega chi U and the critical LYZ equation. This is theta omega chi U equals pi. If we now redefine theta omega chi U equals the sum of arctangent lambda I from 1 to n, then the critical LYZ equation becomes this equation. Theta omega chi U equals n minus 2 times half pi, since arctangent lambda I equals half pi minus arctan lambda I. Malina, Minashin, Moore, and Strominger derived the L-wise equation from D-Broglie supersymmetry. The phase parameter theta encodes the supersymmetry breaking threshold. The critical case theta equals n minus 2 times half pi marks the boundary between BPS and non-BPS configurations, a natural locus for wall closing phenomena. As explained in Li Yang's comprehensive survey, the Thomas-Yau conjecture processes that the existence of special Lagrange representatives in a given Hamiltonian isotopic class should be governed by stability conditions in the derived Fourier category. The L-wise equation is the mirror counterpart of the special Lagrange equation on the A side, with the phase parameter theta playing the role of the stability angle. Collins, Jacobi, and Yau suggested studying the L-wise equation when theta is less than or equal to n minus 2 times half pi. This was later explicitly posted as a question by Li Yang, because resolving it is essential for the L-wise equation to induce a Brillouin stability condition on the bounded derived category of coherent shifts on X. Recently, we have solved the critical L-wise equation. Now, the subsolution condition is this condition. Minimum over J of the sum over I not equal to J of arctan lambda I chi U underline is bigger than n minus 3 times half pi, which is equivalent to the following two conditions. The first condition is theta omega chi U is bigger than n over n minus 1 times n minus 3 times half pi. And the second condition is this: the imaginary part of the NN form, chi U plus the square root of minus 1 times omega to the n minus 1 is a positive n minus 1 form. So this is our main theorem. Let S omega be a compact Kähler manifold and chi cross real 1 form such that the principal augment of this complex number is pi. Then the critical L-wise equation emits a unique smooth solution U if it has a subsolution. When theta 0 is less than n minus 2 times half pi, does the L-wise equation have smooth solutions, or C1 alpha solutions, or even Lipschitz solutions? For comparison, in the special Lagrange equation in Rn, interior Hessian estimates for critical and supercritical cases were proved by Wang Long and Yuan in 2010 and Wang Yuan in 2014. For theta 0 is less than n minus 2 times half pi, C1 alpha solutions were constructed by Nadirashvili and Walad in 2010 and Wang Yuan in 2013. Recently, Mooney Savin in 2024 obtained a Lipschitz solution that is not C1. So we can ask the same question for the L-wise equation. Our proof uses a perturbation method. We consider the family of equations of these equations. Theta omega chi U t plus t omega equals theta t, the perturbation equations. For small t, we verify that there exists a uniform constant C, positive C, such that Ct is in the open interval. This open interval, n minus 2 times half pi plus C2, from this to n minus 2 times half pi plus 2Ct. for small positive t. Ct is strictly greater than n minus 2 times half pi. So these equations are supercritical. We also prove that the given subsolution of the critical L-wise equation is also a subsolution of these perturbation equations for small positive t. So we can use Ling's result. We obtain the smooth solutions ut to the perturbation equation. Then to pass to the limit t goes to 0, we need uniform C2 alpha estimates for ut that are independent of t and 1 over theta t minus n minus 2 times half pi. So we can obtain this estimate. Under the same assumptions, there exists uniform constant C and T0, such that for any T in the open interval from 0 to T0, the C2 alpha norm of UT is less than or equal to C. Thus, the family UT is pre-compact in C2 alpha, and a subsequence converges to a smooth limit, which solves the critical equation. According to Jacobi, the C0 estimate of UT is uniformly bounded. The C0 norm of UT is uniformly bounded. Their results also imply that the C2 alpha estimates can be reduced to proving uniform complex Hessian estimates. So our main contributions are the proof of uniform complex Hessian estimate of Hermite type, supremum over x of the norm of square root of -1 times partial by u with reverse omega is less than or equal to constant c times 1 plus the supremum over x of the square norm of partial u with reverse omega. And the proof of a uniform gradient estimate using a blow-up argument of linear collage. This strategy was done successfully for the complex Hessian equation on Kelly manifolds by Hermite and linear collage. Hermite for the complex Hessian estimate and linear collage for the for the gradient estimate. Zanderkai and Collage independently solve the Hermitian case. However, the gradient estimate is more subtle here. If it fails, a blow-up procedure produces a bounded non-constant C1 function V on Cn that in the sense of currents is the weak solution to one of the 3 equations. The first equation is sigma n of -1 partial V equals 0. The second equation is sigma n -1 of the square root of -1 partial V equals 0. Or the third equation is this is the third equation. Sigma n -1 plus sigma n equals 0. Here sigma k is the k Hessian offlet of square root of -1 times partial V on Cn. The first 2 cases are already known to force V to be constant by Liouville type theorems. But the last case, this case is new and requires a corresponding Liouville type theorem. So note that in the blow-up limit, V plus the square norm of Z is purely subharmonic, and Laplace V is uniformly bounded in the weak sense. When following the argument of linear collage, we need to show that the standard modification of V is subsolution, and this modification of V epsilon square is also subsolution. Here V epsilon is the modification of V. To address this issue, our key observation is the following. A smooth function V on Cn satisfies this equation. Sigma n minus 1 plus sigma n equals 0. If and only if the function W defined on Cn plus 1, W equals Vz plus the square norm of Zn plus 1 satisfies this equation. Sigma n of square root of minus 1 times partial by W equals 0. So we can reduce this equation to this equation. Based on this observation, we use potential theory to obtain the required Liouville type theorem. This theorem. Let V be a C1 and n minus 1 subharmonic function on Cn, and V plus the square norm of Z be a purely subharmonic function. Suppose the C1 norm of V is less than or equal to C, and the Laplace V is less than or equal to C in the weak sense. If V is the weak solution in the sense of current and viscosity subsolution to this equation, then V must be a constant. So we need these conditions. So the natural question is, can one use purely potential theory to weaken the conditions in this theorem? We can use the same technique to prove that a certain weak solution of this equation on Cn is constant. Here is the sigma k and the sigma k plus 1. So the question is for any k, k and L, k is bigger than or equal to 1, k less than L is less than or equal to n. There's a certain weak solution V of this equation on Cn constant. Finally, we find some applications of the main result. In general, the critical L-wise equation has this form. Sigma n minus 1 of chi u equals the sigma n minus 3 of chi u minus sigma n minus 5 of chi u plus the. When n equals 3, the critical L-wise equation is just the two Hessian equation, sigma 2 equals to 1. Our theorem gives a solution and weaker conditions than those by Swinwei in 2017. So this is the current. Let X omega be a compact Kähler manifold with dimension 3. And chi across the real one form satisfying these conditions. The first condition says that chi with omega is a positive 2-2 form. Second condition is this integral of chi square with omega equals the integral over x of omega 3 and omega cubed. And thirdly, this inequality also you need this inequality. Then there exists a unique smooth solution here solving the Hessian equation, two Hessian equation satisfy these conditions. For n equal to 4, the critical L-wise equation becomes the Hessian quotient equation. Sigma 3 equals sigma 1. Another consequence of our result is to solve the above Hessian equation, quotient equation in dimension 4 under weaker conditions than those by Swin and Stickit. So this is our second correlate of our main theorem. I'll stop here. This is some Hessian quotient equation. Well, I'll stop here. Thank you very much.
Okay, thanks, Professor Fu, for the next talk. Okay, so are there any questions?
There are two situations in your talk where there has appeared a balanced class, so the n-1 power of some 1 class to be positive. And I wonder, is there any significance of that? I mean, you had that in one of the main theorems.
Balance.
Yeah, in one of the main theorems, you had that the chi-u need to be balanced or something like this.
No.
What is the hypothesis? And you had it also in the previous to the last theorem, in the case n equals to 3, you also had that chi wedge omega is positive, and I wonder what is the meaning of that? How does this appear in the
So this condition?
No, in the previous term. Here, chi wedge omega positive.
This is the balance metric chi wedge omega, because this is the positive 2-2 form and it is crossed. This is the decrossed positive 2-2 form.
And my question is, what is the significance of these 4 equations? Why do you need a balance metric in this picture?
Sorry.
And before you also had a similar condition for the n-1 power of a combination of omega and chi to be positive. So I wonder what is the significance of that.
So chi is not positive.
Okay.
But chi wedge omega should be we need this condition.
Okay.
Okay, so maybe let's start the next talk. Okay, let's thank Professor Fu again.
因为我也听懂。他就说我说这种的英语讲太快，我也听不懂。他问你就是说那个对。Slowly. 差不多开始吧，早点结束。4点半啊，4点半，4点半啊，没事，提前开始，我们提前走吧。
Okay. Our last speaker is Professor Xiaogui Yang from Tsinghua University, and the talk title is the prescribed Hermitian-Yang-Mills tensor equations from Calabi-Yau to Ulrich-Yau. Okay. Let's welcome.
So, okay, I would like to thank Professor Xiao Jian for the introduction and also to the organizers for the invitation. Today, I will present a joint work with Professor Yao and Mingwei Wang and Xiongzhi Yao about the prescribed Hermitian-Yang-Mills tensor equation. I add a subtitle called From Calabi-Yau to Uhlenbeck-Yau. In fact, we will say that this equation is very similar to Calabi-Yau equation and also closely related to the Hermitian-Yang-Mills equation. That's the Uhlenbeck-Yau solution to the stable bundle version of matrix. Okay. The plan. So the first, I will state the main results. In the second part, I will give the motivation for this problem. In fact, it is motivated by the concept called RC positivity in algebraic geometry. In the third part, we get some motivations for the technique. In fact, we obtained a vector bundle version of Gauss-Schwarz lemma. For the first part, I will give a sketch of the proof. In the last part, I will state the main results for the parabolic version of such results, just because the prescribed Hermitian-Young-Mills equation is an elliptic equation. So we can also consider the parabolic version. We have many speakers, including Professor Yao, talk about the history of the Calabi-Yau theorem. It's well known that if Mg is a compact Kähler manifold, its rich curvature class represents the first chain class of the MB manifold. So it carries the many important geometric and also topological information of the manifold. The converse means given a real closed 1-1 form omega representing the first chain class, whether there exists the Kähler metric with rich curvature matching omega. This is the content of Yau's solution to the Calabi conjecture. Okay. In fact, this is the matrix equation just because this omega is a 1-1 form, is a matrix, n by n matrix. So by using d-bar lemma, this equation is reduced to a class of complex Monge equation. So here, the variable here is phi. F is given by the difference of a rich curvature omega g and also this capital omega. So this is a scalar equation. This is a scalar equation. The solution to this, the Calabi conjecture opens up a new world of fantastical applications in geometric analysis, algebraic geometry, mathematical physics, and many other fields, as indicated by Professor Yao's talk. Okay, there are some other versions like general Hermitian versions of Calabi-Yau's theorem given by the works of Zaghli-Hedy, Tosadi, Wenkov, and also some other. Okay, there are also some similar equations like the Fu-Yau equation, just the Professor Yao Fu talked about, and a K-Hessian equation, and also form time equations and similar. Okay, this is the first one is the Calabi-Yau equation. Okay, next we talk about the Hermitian-Young-Mills equation. So it states that this is the theorem given by Uhlenbeck-Yau for the Kähler case and the Donaldson for the projective case. Okay, it states that for a stable holomorphic vector bundle E over a compact Kähler manifold, this bundle is stable, is in the terminology of algebraic geometry. Okay, then there exists a unique Hermitian-Einstein metric up to scaling, satisfying this equation. This is the equation. This is the Hermitian-Einstein equation or Hermitian-Young-Mills equation. Here, notice that here the RH is the chain curvature of the Hermitian holomorphic vector bundle EH, and that constant lambda 0 has a transparent formula like this. Okay, this constant is fixed. Okay, so that means by using this algebraic condition, Uhlenbeck and Yau can solve this equation. In fact, this equation is an elliptic equation system. It's a matrix equation. In particular, there's an important application. That means stable vector bundles has a very beautiful chain number inequality. The identity holds if and only if this bundle is projective flat. Okay. Together with results by some elementary results by Kobayashi and Wook, this establishes a precise correspondence between algebraic geometric notion of stability and also the existence of Hermitian-Einstein metrics. Okay. Later, this was generalized to the Hermitian setting through the work of Junli and also Professor Yao. This Hermitian-Einstein correspondence forms a core motivation behind Yau's original conjecture, which addressed Kähler-Einstein metrics existence on Farlow manifolds should be equivalent to some stability on compact Kähler manifolds. This conjecture is proposed in 1990. Okay, your survey paper, Okay. This is about the Calabi-Yau theorem and also the Uhlenbeck-Yau theorem. The main result we want to present today is the following vector bundle version of the Calabi-Yau theorem, which addresses the prescribed Hermitian-Yang-Mills tensor problem for holomorphic vector bundles. That means, given a tensor in this space, this is the tensor space, whether we can find some smooth Hermitian metric H such that this equation holds. That means we replace the right-hand side of the Hermitian-Yang-Mills equation, right-hand side, by a given tensor P. So this is called the prescribed Hermitian-Yang-Mills equation. Okay, prescribed Hermitian-Yang-Mills equation. In general, this equation is not solvable. Means there should be some abstractions for P or for the geometry of the n-beam vector bundle and also n-beam manifold. Okay, so we add the condition that if E is holomorphic vector bundle, suppose that there exists some smooth Hermitian metric such that this curvature tensor, we call it Hermitian-Yang-Mills tensor. Okay, this tensor for the Hermitian metric H is a positive. Then for any Hermitian positive tensor in this space, this equation has a unique smooth solution. That means it exists and unique, it's smooth. Okay. We have to mention that this theorem also holds in very general case. For instance, Higgs bundles over complex manifolds. This analogs to the works of Tosadi, Wenkoff, and also Liao, and also Simpson's similar work. Okay. On the other hand, both the conditions, the curvature condition positivity, and also the prescribed tensor positivity can be relaxed just for the need of the presentation as just present the simplest case here. Okay. The key part is the C0 estimate, for this equation. This is in fact established by a new comparison principle. The C0 estimate is established by a new comparison principle. We will see that. Okay, let's compare a little bit. The Hermitian-Einstein equation here, number 5, is a homogeneous elliptic equation system. It's about solving a matrix equation. Okay, it is solvable if and only if E is polystable. It is well known. This is the Uhlenbeck-Yau's result. The second part, the prescribed Hermitian-Yang-Mills equation is inhomogeneous elliptic equation system. Just because the right-hand side is prescribed and is not scaling invariant. It's not scaling invariant. We show that it is solvable for some positive P if and only if E admits some Hermitian metric such that this tensor is positive. Means if you have one positive curvature, then for any positive tensor, it can be recognized as the curvature tensor of some Hermitian metric. Okay. For a very special case that E is a line bundle, this is in fact a type of Kasdan-Waller equation in Riemannian geometry. Because on line bundles, all Hermitian metrics are conformal to each other. Okay, that means if we want to find a solution, then we need to find a smooth function. This also, the equation looks like this. Okay, the equation looks like this. This is a reduced equation. Here, F and G are positive. Yes, okay. So this also gives an alternative proof of the Kasdan-Waller theorem in this case. This theorem is proved in 1970. Okay, 1970. Okay, let's recall the background why we consider such equations. So a line bundle L is called a positive. This part is introduced by Professor Xiang Yuzhou and many speakers. Okay, we just briefly recall it. A line bundle L is called positive if it has a very smooth metric H such that its rich curvature, it is a 1-1 form. 1-1 form, we can translate it into a matrix, M by M matrix. It's just say it is a positive definite. Then there is a well-known Kodaira's theorem that if L is a Lie bundle over a general compact manifold, then we have this version of Kodaira vanishing theorem. Here Q is from 1 to N. The proof is well known that is based on the Kodaira Buchler formula on compact Kähler manifolds like this. So we have two different kinds of Laplacian operators. Then the difference is the contraction of the curvature. Okay. A Lie bundle is called RC positive. Here is something a new terminology, but a very simple terminology. RC positive if it has a smooth metric such that its curvature has at least one positive eigenvalue at every point. Just like, okay, M by M matrix is a positive definite if it has M positive eigenvalues. It is called RC positive if it has at least one positive eigenvalue. I think this should be the weakest positivity in some geometry. Okay. So we also obtain the following vanishing theorem. If L is RC positive Lie bundle over a compact complex manifold, then its dual Lie bundle has no holomorphic section. By cell duality, we can show this type of vanishing theorem. Okay. So by using these vanishing theorems, we can have the following results. The first one is called Gardin-Cell-Grossetti Kodaira theorem. It's very fundamental in algebraic geometry. It says that we want to see some properties of this Lie bundle. We can test by some functional analysis. That means for any coherent shift f on x, if there exists a positive integer, the lower bound such that if m is bigger than m0, then we have a type of Kodaira vanishing theorem. The Kodaira vanishing theorem says that if it's positive, then we have vanishing theorem. Okay, that means we have a functional version of vanishing theorem, then it can imply that L is positive. That means the rich curvature has m positive eigenvalues, which says that if there are n vanishing theorems, then the rich curvature has m positive eigenvalues. Okay. The equivalence of 2 and 3 is the famous Kodaira embedding theorem. So by using the concept of RC positivity, we established a dual version of the Gardin-Cell-Grossetti Kodaira theorem. It states that if there is just one vanishing theorem, then the rich curvature has one positive eigenvalue. Okay, this is a dual version. So let X be a projection manifold of dimension n. If for any coherent shift, there is just one vanishing theorem we stated before. Okay. Yes. Semi-stable. Yes. With Trivison class. Yes, the first class. Probably you are right. Yes. This. Yes. Yes, I know your point. But here, the key point is functional analysis. This is for any coherent shift, it is true. This is just for. This the functional is much more powerful. Yes. This is the, okay. We will explain a little more about this point. Okay, later. Yes. Okay, so we get a dual of the Gardin-Cell-Grossetti Kodaira theorem says that if there is one vanishing theorem, we can show that the dual Lie bundle is not pseudo effective, which is equivalent to say L is RC positive, means this rich curvature has at least one positive eigenvalue. In fact, we can show Part 2 and part 3 are equivalent on very general compact complex manifold. We do not need the projective or killer condition. So as an application of these results, we get some applications in differential geometry. Let's recall the following result of Yao. In fact, it's a consequence, a straightforward consequence of the Calabi-Yau theorem. It says that if an algebraic manifold is final, that means there are many definitions. Here, for instance, we call the first chain class is positive. Then there exists a Hermitian metric such that its rich curvature is positive definite. Here, Hermitian and Kähler are equivalent just because we can use Yau's theorem to reproduce from one to the other one. Okay. So here we obtain an analog for unit-root manifolds based on the result of Murray or BDPP, the theorem of Bergson, Desmahis, Paul, and Pitnell, and also Yau's solution to the Calabi conjecture. We can prove the following results. X is a unit-root. This concept means at each point there is a rational curve, or says that the manifold is covered by rational curves. Here, rational curve means the holomorphic image of CP1. X is unit-root is equivalent to say that there exists Hermitian metric such that its rich curvature is RC positive, means the matrix has at least one positive eigenvalue at each point. Okay, we know unit-root manifolds has a model just like a CP1 product with any projection manifold. So that the CP1 is the model of the positive eigenvalue. Okay, but we know this definition is more or less pointwise. If we want to find such a metric, we need to solve some PDE. In fact, this is by using conformal geometry. Okay, we can solve this equation just because we have one positive eigenvalue means we can take a trace and get an elliptic equation. Okay. Let's recall something in algebraic geometry. Unit-root, we talked about that, is covered by rational curve. Final means the first chain class positive. There is a concept between final and unit-root called rationally connected. We know what's called connected, right? 2 points, we can find a connected path from 0 to 1 to connect these 2 points. Rationally connected means for any 2 points, it can be connected by some rational curve. There is a very natural relation, means final manifolds is the smallest category. We have a bigger one called rationally connected. The unit-root is the largest category. Okay, so we have Yau's results says that we have a perfect correspondence between algebraic geometry and differential geometry by using rich curvature positive. And the unit-root will also get a similar results. So it's a natural question to propose a differential geometric concept for rationally connected manifolds. This is why we call it RC positivity. Okay, so we just improve the definition for line bundle. We can define RC positivity for vector bundles. It's a very natural extension of that definition on vector bundles. Okay, so for holomorphic vector bundle, we call it is RC positive. That means for each vector along the direction of vector bundle, means we fix the vector bundle. Then the chain curvature now is a 1-1 form. We say that if there exists some eigenvector v or just a vector u such that this pairing is positive, this is equivalent to say that if you fix some v, then this 1-1 form has at least one positive eigenvalue. Here, the vector u may depend on the vector v. If it is independent on v, this is called a uniform RC positive. This is a stronger notion. This is a slightly stronger notion. Okay, so a holomorphic vector bundle is called uniform RC positive. Means there is a universal vector u universal vector U such that for any non-zero vector V, it is positive. In fact, this is a translating of a concept in algebraic geometry called very free rational curve. This is a pointwise version of very free rational curve in algebraic geometry. Okay. So here, if each line bundle, they are equivalent just because there is only one direction. Okay, let's look at the first result along this direction. We can show if a compact Kähler manifold X has uniform RC positive tangent bundle, that means it possesses a Hermitian metric, not necessarily Kähler. Okay. Then we can show this manifold is projective and rationally connected. In particular, we get some information on its topology. It is simply connected. Okay. In fact, by using RC positivity, we can show more. We can show if all pieces of its wedge product are all RC positive, okay, then we can get the same result. X is projective and rationally connected. In particular, it's simply connected. In fact, we can propose the following conjecture. This is the motivation of our solving equation technique. We want to characterize rationally connected manifolds by using uniform RC positivity. We want to show the converse. The converse is true. If X is rationally connected, we want to show the tangent bundle is uniform RC positive. Or there exists a Hermitian metric G such that this Hermitian Yang-Mills tensor is positive. It is different from the first chain curvature. First, the ridge curvature is positive. This is the second one. Okay, so it's different. We want to show all of these are equivalent. Okay, in fact, from 1 to 2, we can show a Fenster metric such that the Fenster metric is uniform RC positive, but the Fenster metric is far from Hermitian metric. Okay, this is just one motivation. Okay, let's focus. Okay, let's mention Yale's open problem. Okay, in Yale's problem section, this is proposed in 1982, different from the 1991. Okay, there are 120 open problems in this open problem section. Okay, Yale conjectured that if X is a compact Kähler manifold, if it has a positive holomorphic section curvature, then X must be projective and rationally connected. This is Yale's conjecture in 1982. In fact, we can solve this conjecture for generality and show that if X omega is compact Kähler manifold with positive holomorphic section curvature, then we can show its holomorphic tangent bundle is uniform RC positive. In particular, by our previous results, we can show X is projective and rationally connected. Okay. There are many extensions of this result, and by many mathematicians like Professor Fangyang Zheng here and also Li Lei. Okay, they can extend the result to some refined curvature notions like orthogonal ridge curvature and some others. And by using the idea of RC positivity, Matsumoto can prove these results for quasi-positivity on projective manifold, and Xi Zhang and Shi Zhang can prove this for general Kähler case, means if it is a compact Kähler manifold with holomorphic section curvature quasi-positive, then can show the same results. Okay. Okay, let's recall the motivation of our background. The byproduct, we also obtain the following results, analogous to Singer's theorem and also Yale's theorem. We get a very interesting results. Looks like a differential geometry. Okay, let MG be a compact Kähler manifold. If the holomorphic tangent bundle is uniform RC positive, then fundamental group is trivial. How can we prove this result? Okay, we get this result. Let's recall, if MG is a reversible compact Riemannian manifold even dimension with sectional curvature positive, then M is simply connected. This by using second reversion formula. And also Yale's result, all final manifolds are simply connected. This by solving the Monge-Ampère equation, and by Meyer's theorem, the fundamental group is finite, and then by Riemann-Roch, Riemann-Roch to the carving, lift to the carving, then we can show the curve must be a simple curve. Then it is simply connected. Okay. However, This theorem is achieved by using algebraic geometry. In fact, we use Kampala and also Clark-Milka-Morris results. All rationally connected projective manifolds are simply collected. We use this result. So this result looks like a consequence in differential geometry, but we use a technique in algebraic geometry. So natural question, is there a differential geometric approach? For instance, by using second variation formula or like Yale's result, solving some PDE to solve this result. So we want to see the behind differential geometry and this theorem. Okay. On the other hand, we also get some rigidity theorems similar to Yale's rigidity theorem, Newell theorems, by using algebraic geometry. For instance, we know there is a very famous rigidity theorem says that a holomorphic map or harmonic map from positive curved manifolds to negative curved manifolds must be a constant. Positive curved to negative curved must be a constant. Okay. In fact, we can get a slightly weaker version that if the holomorphic tangent bundle is uniform RC positive or holomorphic sectional curvature is positive, the target manifold has negative sectional curvature or very general, it's hyperbolic in the sense of Brody or Kobayashi. We can show this must be constant. Okay, this is by using rational connectedness. So is there an approach by using Yale's Schwarz-type lemma or maximal principle? This is our motivation to do this. Okay, let's recall Yale's maximal principle. Okay, it states that if F is a holomorphic map between two complex manifolds, the domain manifold has rich curvature bounded from below by a negative constant, and the target has negative holomorphic sectional curvature bounded by a negative constant. Then we have the estimate such that the pullback metric is less than or equal to lambda over k times omega g. This normalized. Okay. This follows by an elliptic equation. Okay. Elliptic equation. There are many important generations of this result by the works of Chen Zhihua, Zheng Shaoyuan, Lu Qiken, and also Royden, recently by Li Lei and also Fang Yangzhen, by Chen and Nie. Okay. Let's briefly recall the comparison theorems in differential geometry. It says that if the rich curvature of a complete Riemannian manifold is greater than or equal to the curvature of the sphere, then the diameter is less than that of the sphere. Shaoyuan's result says that if the diameter are the same, then they are asymmetric. And also the volume comparison theorem, that the volume of this manifold is less than or equal to that of Sn. If the identity holds, then they must be asymmetric. Yes? Which one? Here, yes. Yes, here I mean Zheng Shaoyuan's result, if they are the same, then they are asymmetric to each other. And also this is rigidity. This is a very classical rigidity result. Okay, so motivated by such results, we want to develop the geometry and analysis on RC positivity. So in fact, we obtain a vector bundle version of the Schwarz lemma, which works for both positive curvature and also negative curvature in the setup of RC positivity. Previously, we know Schwarz lemma works for negative curvature, just like the Schwarz-Pick lemma, right? Yale's Schwarz lemma works for negative curvature. We show that this can work for positive curvature. On the other hand, we know the comparison theorem works for positive curvature. We can show those can work for negative curvature. So the first result we want to mention is the following comparison results. Let M be a compact complex manifold if there are two Hermitian metrics such that the curvature of H is less than that of G in the sense of RC positivity. That means for any non-zero V, there exists some W such that this inequality holds. And also this curvature is positive. Then we can deduce that omega h is less than or equal to omega g. In particular, we have the diameter comparison and also the volume comparison. That means we just need a very few vectors, not like a rich or some others. We very few. For any V, we just need one vector W. That's enough for this comparison. Okay. Another feature of this result is that there are no precise curvature bounds in our setting. Means we do not need to compare it with classical space like Sn or Cpn or something. Just the two straightforward metrics. Okay. As an application, we get the following strong rigidity for Hermitian matrix. That means if two curvatures are the same in the sense of RC positivity, then the matrix are the same. This I call the strong rigidity. Means the curvatures are the same in very few places, then the matrix are the same. This result can be regarded as a unique list of solutions to PDEs with very weak ellipticity. This is even new in the Kähler setting. Indeed, the Calabi-Yau equation we mentioned before is an elliptic equation in the sense of linearization. It's like this. Okay, this is elliptic one, but here is very weak. Okay, RC positivity is much weaker than positivity of the rich curvature. Okay. So we want to mention the following vector bundle version of the Schwarz lemma. Okay. If F is a holomorphic map between two Hermitian manifolds, there are two Hermitian holomorphic vector bundles on M and N respectively. Then we can pour back the holomorphic vector bundle E2 to Mg. Then we have a setup on the single manifold Mg. Okay, there are two vector bundles E1 and E2. Then we say that if E1 is RC positive and E2, the curvature of E2 is negative, is less than or equal to kappa times the curvature of E2, then we can show that the metric, the pullback metric, is less than or equal to kappa times E. Okay. Okay, it's a Tsinghua style. Okay. Okay, we just briefly mentioned the proof of this result, how to prove the vector bundle, this vector bundle version of the Calabi-Yau theorem. Okay, the key ingredient is established by the following comparison principle. This is established by the following comparison principle. It states that if E is a holomorphic vector bundle over a compact Kähler manifold, if H and H0 are two Hermitian matrices such that the curvature, the Hermitian Yang-Mills tensor of the first metric H0 is positive definite, and we can compare both them, means the curvature, that curvature of H is less than H0. These tensors are all in this space. Then we can conclude that H is less than or equal to H0. Okay. This theorem also holds for Higgs bundles over non-Kähler manifolds. We can prove that. Yes. Okay. So let's recall how to use this comparison principle. Okay. The first one is uniqueness. If there are two Hermitian matrices such that the curvatures are the same and positive, then we can show they are the same. This is by symmetric property. Then we can show they are the same. Okay, this is the first one. We can show this by show the uniqueness. The second part is the most important one. We can get the C0 estimate. As we know, in the proof of the Calabi-Yau theorem and also Hermitian-Einstein, the Uhlenbeck-Yau theorem, and also Donaldson's proof, the most hard part, most difficult part is the C0 estimate, is the C0 member. In fact, we can get C0 estimate by this theorem. Means we can scale. Means the curvature of H is less than or equal to that of lambda times that of H0. Then we can show H is less than or equal to lambda times H0. So this gives the proof of C0 estimates in solving that prescribed Hermitian-Young-Mills equation. This is the most important step. That's the uniqueness and also the C0 estimate. Okay. So as inspired by the prescribed Hermitian-Young-Mills equation and also the comparison theorem, we can get similar results as the classical applications of Calabi-Yau theorem and also Donaldson-Uhlenbeck theorem. We can get some number inequalities. Here, the condition is that the curvature is bounded between A times H0 and BH0. If the curvature, the Hermitian-Young-Mills curvature, is bounded by A and B, then we can get the classical number inequality, quantitative number inequality. Here, the right-hand side, we have B minus A squared. If it is Hermitian-Einstein, that means if A equals B, then the right-hand side is 0. Then it is a classical number inequality divided by Uhlenbeck-Yau, Donaldson-Uhlenbeck-Yau. We can also get the following version for compact Kähler manifold. If the rich curvature is bounded by A omega g and B omega g, and then we can get this so-called Bogomolov-Mialka-Yau inequality for the surface case. This is also result for general case. Okay, we can show that. So if A equals B, then it's Kähler-Einstein. Then we get this. The coefficients are different. Okay, so we get the same thing. The quantitative number inequality. Okay, let's go through the proofs. Okay, the proofs. I just add a subtitle called "From Calabi-Yau to Uhlenbeck-Yau." In fact, this proof is following Yau's proof of the Calabi-Yau conjecture. We use the continuity method. Very straightforward continuity method. Okay, so we have two spaces. That Hermitian space is the smooth Hermitian tensors on E. Here, Hermitian plus means the matrix, Hermitian matrix. Then we define a Hermitian-Young-Mills map from matrix to Hermitian-Young-Mills tensors by this one. Okay. Here we add the condition H0 such that the contraction is positive. Then we get a map G from the inverse to Hermitian plus, just because this space is a subspace of Hermitian E. So here, this set is non-empty because we have this assumption. We will show that this map, this Hermitian-Young-Mills map G, is in fact a bijection. If it is a bijection, then we can find the solutions for every positive tensor in this set. Okay, so how to prove it is a bijection? The injectivity, we show that is given by the comparison principle. For the surjectivity, we show the image of that map. This is the image set. We show it is both open and closed in Hermitian E plus with respect to the C infinity topology. We show it both open and closed. Okay, for the openness, this is very close to Yau's solution to the Calabi conjecture. We just do the linearization of that map G and say, okay, it's an elliptic and also positive definite, so we can solve it by implicit function theorem. This is the first step. For the second step, for the closeness, okay, we follow Yau's results. At first, we do the C2 estimate and then do the C3 estimate. For C2 estimates, we need the help of C0 estimate. But here, we call C0 is equivalent to Yau's C2 estimate. Okay, so we have a uniform C0 estimate given by the comparison principle we mentioned before. For higher order estimates, we just get a C1 estimate. This is very similar to that in the proof of Yau's Calabi-Yau theorem, the C3 estimate. Okay, and then we use WKP and CK estimates for elliptic equations. We obtain smooth solution, just this picture. Okay, if we have a distillation P, we have a sequence converges to that P in the infinity sense, then we find some smooth metric, just this picture. Just because this P is given, so we can say when M is not enough, then the curvature is very close to P. That means the curvatures are very close to each other, then we can do the C0 estimate. We do the C0 estimate. This is the sketch the proof of the prescribed Hermitian Young-Mills equation. This is the proof. I think this looks very not say elementary, but say very close to very old fashions. I mean, this proof should go back to 1970s or around. Okay, no new tools at all. We use very elementary tools. Okay. In the last part, we're just doing some routine sense. Means we propose something called prescribed Hermitian Young-Mills flow, as analogous to the Hamilton's ridge flow and the Taylor ridge flow proposed by Professor Huaidong Cao here, and also the Chen ridge flow proposed by Tosadi Unkov and Gill, and also Donaldson Hermitian Young-Mills flow, and many other important flows. We propose the following prescribed Hermitian Young-Mills flow. That means we prescribe that P, prescribe this P, and running this flow and running this flow. The key feature is that by using the flow, we can solve the prescribed Hermitian Young-Mills equation, solve this equation for more general P under Vival's differential geometric and algebraic geometric conditions. Okay, for instance, in fact, we get very general results, but for simplicity, we just list some simple results here. The first one, okay, the first one is also the joint work with Professor Yao and my student Zhi Yao Xiong here. Okay. Let E be a holomorphic vector band over a compact Keeler manifold. If the curvature is positive, then for any quasi-positive P and any initial metric, then this prescribed Hermitian Young-Mills flow converts to a smooth Hermitian matrix such as this equation. Okay. And this part is, as we know, for the parabolic case, the proof is harder than the elliptic case, just because we should do first, for example, the C0 estimate, and also we should consider the long-time convergence. Here, the C0 estimate is established by a parabolic comparison principle, which is a parabolic version of our comparison principle in the elliptic case. Okay. Next one is very similar to the Donaldson-Woodenberg-Yau theorem. We show that if E is holomorphic vector bundle, suppose that for any proper torsion-free coherent sheaf, the degree of F is less than degree of E, then for any positive P, this prescribed Hermitian Young-Mills flow converts to a smooth Hermitian metric solving this equation. Here, we replace the curvature condition by this algebraic condition. Okay. I have to mention that the proof of these results, the key part is always the C0 estimate. This is established by the parabolic comparison principle for the lower uniform bound. And for the upper uniform bound, we have to use the Woodenberg-Yau theory. Just doing the contradiction method, assume it blows up, and then we can construct some weakly holomorphic section, just like Woodenberg-Yau technique. Okay, this part is very deep. The Woodenberg-Yau part is very deep. Okay. So thank you very much. Yes.
Thanks for the inspiring talk. Okay. So
how about the last part with the parabolic case? we are working with no zero Higgs field.
Yes, it works for Higgs field.
It's the same.
Same thing. Just like our previous results, our first results, solving the prescribed, we also works it for Higgs bundles over non-killer manifold. We can solve all of them. Yes, the estimates are very similar. Just we need to keep the torsion term. There are two kinds of torsion terms. The first torsion is given by Higgs field. The second torsion is by the manifold torsion when each is non-killer. We can package it together and doing the C0 estimate and also the Calabi-Yau C3 estimate.
Okay, this parabolic structure means that you have the singularity of your metric along some normal crossing divisor.
Oh, this is a different story. This is a different story.
It's different story.
Yeah.
It's not here.
Yeah, not here. Yes, it's a different story. Yeah.
Of this part with the previous part. So in the previous part, you talk about anti-positivity.
Yes.
You want to have a deep proof of the simply connectedness of the.
Yes, you are right. This is a very good question. In fact, all of these conditions are equivalent to RC positivity. This we want to prove. Yes, all this condition is equivalent to RC positivity. This positivity is also equivalent to RC positivity. This is our conjecture. They are all equivalent. Yes. So far we can prove that if this is positive, then it's RC positive. And this if this condition holds, then this bundle E is RC positive. We can show that. Yes. This is why we call it RC positivity. We want to show all of them are equivalent. All of them are equivalent. Yes. Yes.
I'm a bit confused about your proof of the uniqueness of the Hermitian-Mills equation. So suppose you have a polystable vector bundle with positive first-chain class.
Yes.
And there is not uniqueness. It's only uniqueness up to automorphisms.
No. Okay, this result, right?
Yeah.
Okay.
What I'm saying is that if you have a strictly polystable holomorphic vector bundle with
this is different conditions. So here we add the positivity of the curvature. This curvature is not the positivity of the first.
No. But wait. This is why I'm imposing positive first-chain class. So suppose you have a strictly polystable holomorphic vector bundle with positive first-chain class. Then there exists a solution of the Hermitian-Mills equation, but this is not unique. It's unique up to
I get your question.
automorphism.
I get your question. This is a different story. Okay, I can show you. This is the common question. Just because in our tensor case, they are in the space. For example, P is in the space of metric space or tensor space. In general, the general case, just like the Hermitian-Young-Mills equation in some notations used by Donaldson or Yau, it looks like this gamma identity E. This is in the space E star tensor E. E tensor E star. So we use the metric to reason the index. This is different. Okay, this answers your question. So this equation has no uniqueness just because we can do the scaling. This is the Hermitian-Young-Mills equation. We can do the scaling, so the solution is not unique. But for our equation, okay, if you give P, if you scale here, you get a multiple here, but P is fixed. So you cannot get multiple solutions in this case. Okay, this is the key reason. Yes? Yes, this is a very good question. Thank you. Yes. We have several techniques to deal with this case. By elliptic case, we can show this curvature. We show, for example, this one. This one is positive. This is H0. We can ask positive 0. We can just require the first eigenvalue of this vector. Weaker version is the first eigenvalue of this vector is integrable and positive. And for the flow case, we can show if there are two different Hermitian matrices such that H, P that of this P is in this range, then this flow equals plus P with H0 equals given this H0. This flow, this converges in subconverges means the solution may not be unique, but we still can extract some convergent subsequence such that can converge to such P. So this is very general, means that the P need not to be positive, just between, this just using some maximum parabolic maximum principle. So I don't want to write this complicated one. Yes, in fact, this is stronger than the previous one. Yeah. No assumption. But in fact, this is not a. This in fact is a stronger condition just because here you can see here, and this is the restriction. There are some restrictions, just because you have the metric comparison and also the curvature comparison. It is still restrictive. Yeah.
Okay.
Professor, I'd like to ask a question concerning your theorem on CR geometry, CR positivity of line bundles.
Yes.
You proved that the higher tensor power of such a line bundle, the cohomology vanishes,
Yes.
is equivalent to the CR positivity. And does this have a generalization to CR positivity is the positivity of one eigenvalue. So
yes.
if we assume the biggest m eigenvalues are positive.
You mean more eigenvalues, just 2 or 3, something like that? Yeah, this is a very good question. In fact, I have a project on true positivity. So our conjecture is that if it has a, just like the tangent bundle has two RC positive, then it's called a rational surface. It's a theory done by De Jong and Johnson Starr, characterize just the two funnel manifolds. It's a higher funnel manifolds in algebraic geometry, but it's much harder. It's much harder. This is a very good question. We have a project to understanding such problems in algebraic geometry. Yes.
So this is not known yet.
Not known.
Yeah.
It's widely open.
Thank you.
Widely open. So our conjecture is that for two positivity, one positivity just for rational curve, for positivity just for rational surface, to characterize two funnel manifolds. Yeah.
Thank you, Professor.
Okay. What's the questions? Okay, you know, let's thank Professor Yang. Okay.
Thank you. Yeah.
Okay, and let's thank all the speakers. Okay. Yeah.
I'm confused about your